Preparation of phosphorus pentachloride, which is PCl5. Phosphorus pentachloride is prepared by the reaction of white phosphorus with excess of dichlorine. White phosphorus reacting with excess of dichlorine will give us PCl5. It can also be prepared by a reaction of thionyl chloride on phosphorus. When we take excess of thionyl chloride, P4, which means it is white phosphorus, will react with thionyl chloride to give us PCl5 and sulfur dioxide. Properties are: PCl5 is a yellowish white powder and is voiced in air. It hydrolyzes to POCl3 and finally gets converted to phosphoric acid. Two-step reaction for phosphorus pentachloride to convert into phosphorus acid, which is PCl5 reacting with water to give POCl3 and HCl, and then POCl3 reacting with water to give H3PO4 along with HCl. Both of the reaction byproducts are HCl because we have water and chloride in the groups. When heated, it sublimes but decomposes on stronger heating. When we heat it to a certain degree, it will turn into gas, but when we heat it with a higher temperature, it will decompose to phosphorus trichloride. Reacts with organic compounds containing OH group, converting them to chloro derivatives. Methanol plus PCl5. Ethanol plus PCl5 will give us chloroethane, POCl3, phosphoxy trichloride, HCl, hydrochloric acid, and in case of carboxylic acids, ethanoic acid here plus PCl5 will give us CH3COCl, POCl3, and hydrochloric acid. Finely divided metals on heating with PCl5 give corresponding chlorides. Silver, if you heat with phosphorus pentachloride, will get silver chloride and phosphorus trichloride. Tin, if you heat it with phosphorus pentachloride, we will get tin chloride and PCl3. This is the structure in the gaseous state. It is used in the synthesis of some organic compounds, example haloalkanes and the carboxy chloride groups. In gaseous and liquid phases, it has a trigonal bipyramidal structure as shown here. The 3 equatorial PCl bonds are equivalent, while the 2 axial bonds are longer than the equatorial bonds. This is due to the fact that the axial bonds suffer more repulsion as compared to the equatorial bond pairs. In the solid state, it exists as an ionic solid, PCl4 plus and PCl6 minus. These are tetrahedral and octahedral complexes in which the cation PCl4 is tetrahedral and the anion PCl6 is octahedral. This is in case of liquid or solid. Actually, it's in the solid state itself where they are more compact. In liquid, this state of trigonal bipyramidal is somewhat retained. Why does PCl3 fume in moisture? PCl3 hydrolyzes in the presence of moisture to give fumes of HCl. In case of PCl5 as well, it will give fumes of HCl as well. We saw the reaction here. In case of PCl5 two-step reaction, PCl5 reacting with water to give HCl as a byproduct, and POCl3, the second step reaction, also giving us HCl as a byproduct. This is a reaction. It is same case in case of PCl3 as well. And the next example question: are all the 5 bonds in PCl5 molecule equivalent? Justify answer. No, we just read that equatorial bonds are equivalent and axial bonds are not equivalent to the equatorial bonds, but they are longer in length, and we saw that here it is 200 pm, meaning picometer length, and here it is 240 picometer, a little longer, 38 picometer to be exact. This is due to electron 90-degree repulsion from the equatorial pairs. PCl5 has a trigonal bipyramidal structure and the 3 equatorial PCl bonds are equivalent, while the 2 axial bonds are different and longer than the equatorial bonds. As per justification, it is because of extra repulsion faced by the axial bonds. What happens when PCl5 is heated? When it is heated little or in slowly, we can say, it will sublime, whereas if it is heated too fast or with too high of a temperature, it will directly decompose to give chlorine gas and PCl3 phosphorus trichloride. The reaction is given here. Okay, that is the answer for the first intake question. Write a balance equation for hydrolytic reaction of PCl5 in heavy water. What do you mean by that? Hydrolytic reaction of PCl5 in heavy water. I'm not too sure about that. I'll see that later. Now, oxoacids of phosphorus. Phosphorus forms a number of oxoacids. The important oxoacids of phosphorus with their formulas, methods of preparation, and the presence of characteristic bonds in their structures are given in the table 7.5. These are similar to the nitrogen oxide oxoacids. Not really oxoacids, they gave a table, but fine. Oxoacids of phosphorus, and of course this is we have phosphoric acid. This is the orthophosphoric acid, and this is the hypophosphoric acid, the first molecule being hypophosphoric acid, H3PO2. The state is +1, and characteristic bonds in this molecule are, there is one P and OH bond and two P and H bonds. Basically the structure is I'll use word P block elements. The structure of H3PO2. This is hypophosphorus, which we can also call as phosphinic. Hypophosphorus / phosphinic. Structure is P double bond O, POH and H and H. I believe this is the structure of hypophosphorus. The next is, and preparation is white phosphorus with alkali. Any kind of alkali, if we react, we'll get this alkali. We can take it as NaOH. Okay, then orthophosphorus, which is our phosphoric acid. It has, in this case, the oxidation state is +3, and here this is phosphonic. Okay, this is +3. Okay, or +3 is the oxidation state. Here +1 +1 -1 and -2. Should be -1. It is indeed correct, the structure. Anyways, here in this case the oxidation state is +3, and here there are two POH bonds, one PH bond and one P double bond O bond. This is orthophosphorus phosphonic The above one, hypophosphorus, was phosphinic. Here it is phosphonic. It is H3PO3. H3PO3 we can write as PO OH. This is the structure. Oxidation state is +3. Okay, the oxidation state is +3, and the next compound is, and the preparation is P2O3 plus water. That is the preparation method. P2O3 phosphorus oxide plus water. Okay, diphosphorus trioxide with water will give us orthophosphoric acid. Okay, phosphorus, and no, this is pyrophosphorus. Pyrophosphorus, we have a reaction of, just a minute. This pyrophosphorus, formula of H4P2O5. H4P2O5, oxidation state here as well, it is +3, and the structure will be having 2 POH bonds similar to the orthophosphoric acid. 2 pH bonds, but it has 2 pH bonds instead of the 1 pH bond in case of orthophosphoric acid, and 2 PO bonds, P double O bonds, 2 P double bond O bonds, and this is prepared by phosphorus trichloride reacting with orthophosphoric acid. Okay, we are basically adding a phosphorus from the phosphorus trichloride. And hypophosphoric, it is in here hypophosphorus, it is OUS, but in case of phosphoric it is ORIC. It is also a double phosphorus molecule, but here different from the pyrophosphorus is that there are 6 oxygens here, and the oxidation state is increased by 1, 4 POH bonds, 2 P double bond O bonds, and 1 P phosphorus bond. This seems to be an attachment of 2 of the individual molecules or something like that. And the preparation method is hypophosphorus was prepared by white phosphorus plus alkali, but here it is red phosphorus plus alkali. Both are hypophosphorus and hypophosphoric. And the next is orthophosphoric. The preparation method is reaction with water, and in case of orthophosphorus we use P2O3. Here we use P4O10 and plus water, and the formula is H3PO4. Oxidation state is +5. There are 3 POH bonds, 1 P double bond O bond. Preparation, as I said before, it is P4O10, reacting with water. And pyrophosphoric, exact same repetitions, hypophosphorus, hypophosphoric, orthophosphorus, orthophosphoric, pyrophosphorus, pyrophosphoric. And this pyrophosphoric is has two more oxygens than exact same chemical formula, but two more oxygens. Oxidation state is also increased by 2. There are 4 P and OH bonds, 2 PO bonds, and 1 PO and P bond. Heat phosphoric acid. Phosphoric acid, I mean maybe this one. If we heat this, maybe this is formed. Metaphosphoric. This exists in polymeric forms only. It does not exist as a single discrete unit. This metaphosphoric exists as polymers, meaning many of HPO3 will be linked together. Characteristic bonds of HP3 have been given in the table. Okay, there are 3 POH and bonds, POH bonds, P double bond O, and the main linking bond is POP, where it will bond through the chains of the metaphosphoric are formed through oxygen bonding. Phosphorus acid plus Br2. If we add phosphorus acid plus Br2, heat in a sealed tube. Okay, the composite, that is the preparation, and the compositions of oxoacids are interfered in terms of loss or gain of H2O molecules or atoms. Yes, the compositions of oxoacids are interrelated in terms of loss or H2O or oxygen atom. It only depends as loss or a loss of oxygen or water molecules. The difference, if we see in all these molecules, it will be mostly all contain hydrogen, phosphorus. The only difference will be water and oxygen molecules. Here the main base molecule is phosphorus. All have phosphorus molecules. The only difference we see is in hydrogen and oxygen. Hydrogen we will get from water, whereas we will get oxygen separately, where in this case we can get it from P2O3, or here in case of phosphoric acid, and as such. The structures of some important oxoacids are given below. Important oxoacids. Orthophosphoric acid. Okay. orthophosphoric acid. H3PO3. No, it is H3PO4. Orthophosphoric is basically 3 OH molecules and PO bond. It is, I believe, very highly acidic, and this is the pyrophosphoric acid, the POP bond, and here it is the orthophosphorus acid, which has a single H. There is not much difference if you see. And in case of hypophosphorus acid, there are 2 hydrogen and 1 oxygen, and this is the structures of some important oxo acids of phosphorus. Okay, cyclotri metaphosphoric acid is basically metaphosphoric acid. Basically a single units of HPO3 are linked together through PO bond. Basically HPO3, this is a single molecule. There is a single unit or monomer of the polymer chain. Here this is a 3 molecule chain. There are 3 monomers here, and this is also a metaphosphoric acid itself, but here this is the molecule and the O linkage is linear in shape. Here it is cyclic in shape, where it is forming a circle. Here it is linear bonding. Okay, in oxo acids, phosphorus is tetrahedrally surrounded by other atoms. Okay, phosphorus being a central atom, it is of course surrounded by hydrogen and oxygen molecules or atoms. All these acids contain at least one PO bond and one POH bond. Why these are called acids is because this can easily release this H+. It can release the H+ here due to the electronegativity of the P bond. Because of that, it can release H+. That is why we call it as acids. The oxo acids in which phosphorus has lower oxidation state, less than +5, contain, in addition to PO bond and POH bonds, either P bond P, example in this is H4P2O6. This is the pyrophosphoric acid, I believe, right? No, this is pyrophosphorus acid. No. It is hypophosphoric, not pyro. Hypophosphoric. In hypophosphoric, it has a 5 oxidation state. No, there is a +4 oxidation state, but there is a P bond P. That is what they are saying here. There is a P bond P. If these are less than +5 oxidation state, if it is +5, then there are no additional bonds. Or we can see P hydrogen bonds as well in case of hypophosphoric or phosphorus bonds, but not both. Both pH bonds and P bond P are not found in the same compound. These acids in +3 oxidation state of phosphorus tend to disproportionate to higher and lower oxidation states. Okay, +3 oxidation state phosphorus, they disproportionate to higher and lower oxidation state, maybe because +3 is not stable for them. For example, orthophosphorus acid or phosphorus acid, ortho meaning it is a H3PO3 or H3PO4. It's actually H3PO3 acid. On heating, disproportionate to give orthophosphoric acid, phosphoric acid, H3PO4, and phosphine. Phosphine meaning phosphorus hydride. The acids which contain strong pH bond have strong reducing properties. Reducing meaning maybe they can oxidize easily. Thus, hypophosphorus acid is a good reducing agent as it contains two pH bond and reduces, for example, AgNO3 metallic silver. AgNO3 plus water plus hypophosphorus will give us Ag and HNO3 with phosphoric acid. Okay. Acting as a reducing agent, meaning it is giving H. A good reducing agent meaning it is getting oxidized easily. So oxidized meaning it is easily able to remove those pH bonds. These pH bonds are not ionizable to give H plus and do not play any role in basicity. They do not give H plus, meaning I think they will only give free radicals of H1 electron. Only those H atoms which are attached with oxygen in POH bond are ionizable, cause the basicity. Thus H3PO3 and H3PO4 are dibasic and tribasic. The structures of H3PO3 has two POH bonds and H3PO4 3. Basically, how many bonds, POH bonds they are there. How do you account for reducing behavior of H3PO2 on the basis of its structure? In H3PO2, two atoms are bonded directly to P, the phosphorus atom, which imparts reducing character to the acid. Okay. What is basicity of H3PO4? What happens when H3PO3 is heated? H3PO3 is heated, it will disproportionate to give H3PO4 and PH3. This happens because it's a +3 oxidation state, and in the +3 oxidation state they tend to disproportionate to give higher and lower oxidation states compounds. That is the answer to the second question. As for what is the basicity of H3PO3, I don't think it is basic but very acidic, because if we see the structure of the phosphoric acid, orthophosphoric acid, H3PO4, we see that it has 3 OH groups, and due to the electronegativity it can become a PO4 minus ion, BO4 minus ion, which is by giving 3 H plus, so it is incredibly acidic. As for accounting for basicity meaning, I believe it is related to the pH. What is the basicity of H3PO4? It is 3. Yeah, it is extremely weight. Okay, basicity refers to the number of hydrogen ions an acid can donate in an aqueous solution. Phosphoric acid is triprotic acid, meaning it can donate 3 protons. Thus, basicity is 3. Is that? I don't think it's pH. I think, is this basicity relate to normal basic nature or alkaline nature? No, this basicity is like actually a different concept. Basicity of an acid refers to the number of ionizable hydrogen atoms or protons an acid can release, but basic alkaline nature refers to accepting protons or releasing OH minus. This is a different base. It is not alkaline, but it is a new concept. Okay. And as for the question, answer to the question, what is the base city of H3PO4? It is 3. And with this we completed group 15 elements. Group 15 elements have completed, mainly studying about nitrogen and phosphorus, which are non-metals, their reactions, their special compounds, mainly about nitrogen. Nitrogen, we study about nitrogen oxides, nitrogen hydrates, and other reactions of nitrogen, formation of ammonia, compounds of nitrogen like nitric acid, etc. And here we study about phosphine, phosphorus hydride. Then we studied about phosphoric acid, oxoacids, other oxoacids, and I think that is under the 15th group elements. And we study about the allotropes of phosphorus. Nitrogen doesn't have any allotropic forms, but we did read about allotropic forms in phosphorus, which are white, red, and black. And black is divided into black, beta, alpha, and beta black phosphorus. It is just same structure, but difference in it's either discrete in white phosphorus or in packets or in polymers in case of other phosphoruses. We studied about an Ostwald process, Haber's process, Ostwald's process. This is preparation of nitric acid. Preparation of nitric acid, we use Ostwald's process. This method is based on catalytic oxidation of NH3 by atmospheric oxygen. NH3 reacting with oxygen in presence of platinum, RH gauge catalyst, 500 Kelvin and 9 bar will give us nitrogen monoxide and water. And this nitrogen oxide, second step is nitrogen monoxide reacting with water, not water, oxygen again, to give us nitrogen dioxide. This the nitrogen dioxide dissolve in water to give us HNO3 and nitrogen monoxide. This is about nitrogen monoxide. These are the nitrogen oxides of nitrogen basically. This is ammonia and properties, chemical reactions. This is the detection of ammonia. Ammonia, if we can use for detection, where copper, which is blue, which will form a complex if there is copper in a solution, to give us a deep blue solution. And in case of AgCl, it will give us a colorless solution. When AgCl is normally white in color, but we add ammonia, it will form a complex and it will become colorless. This will indicate the presence of silver. And okay, these are the nitrogen oxides, which are mostly acidic with some being neutral, are mostly gases, some are solids. These are the structures and uses of nitrogen, ammonium, HNO3 actually. HNO3 acting as a strong oxidizing agent. The reactions are preparation reaction. Preparation in small scale, we prepare with sodium nitrate reacting with sulfuric acid in lab to give us sodium hydrogen sulfate and HNO3. And in large scale, we use the Ostwald's process to prepare ammonia. We saw two processes here, Haber's process, Ostwald's process. Haber's process is preparation of ammonia and Ostwald's process is preparation of HNO3. Okay. Then phosphorus allotropic forms of white, red and black. Preparation is just with high temperature, sealing it in a container and heating it to specific temperatures. Both the red and black phosphorus will be formed. Alpha black phosphorus will be formed from white phosphorus at 800 Kelvin, whereas beta phosphorus is prepared by, black phosphorus is prepared by heating white phosphorus. Alpha black phosphorus is formed when red phosphorus is heated in a sealed tube at 803 Kelvin, but beta black phosphorus is prepared by heating white phosphorus at 473 Kelvin under high pressure. And these do not burn in air. Phosphine is the phosphorus hydrogen, phosphorus hydride. It is explosive. It can be used in signals. It can be used as smoke screen, etc. Okay. Next is the 16th group element, which is basically which 16 group elements are basically oxygen, sulfur, selenium, tellurium, polonium, and livermorium. Once more, the 16 group elements are oxygen having a atomic number of 8, atomic mass of 16, and sulfur, the next period, atomic number 16, atomic mass 32. The next is selenium. These three are non-metals, with selenium having an atomic number of 34, atomic mass of 79 approximately, and tellurium is a metalloid with having a 52 atomic number, 127 mass number, or 127.60 exactly. And next is metals, starting with metals, 84 polonium and 116 livermorium. Oxygen, sulfur, selenium, tellurium, polonium, livermorium. Once more, oxygen, sulfur, selenium are non-metals, whereas tellurium is metalloid, polonium and livermorium are metals. But I don't think we are going to study about livermorium, and at least is not mentioned. Of totally 1, 2, 3, 4, 5 elements, not including livermorium, and mainly going to study about oxygen, sulfur. Group 16 elements of oxygen, sulfur, selenium, tellurium and polonium. As I said before, livermorium is not included here. Constitute group 16 of the periodic table. This is sometimes known as the group of chalcogens, where the group 15 was called group of pnictogens. Here it is called chalcogens, and the 17th group is called halogens. 18th group is the inert elements or noble gases. Chalcogens, the name is derived from the Greek word for brass and points the association of sulfur and its congeners with copper. It's a name for brass, and also it just says reaction with sulfur and copper. Most copper minerals contain either oxygen or sulfur, and frequently the other members of the group. Basically talking about copper ores. Occurrence. Oxygen is the most abundant of all the elements on Earth. Maybe they did not include nitrogen here. I have a doubt on this statement. Is maybe in all forms they are talking about and not in the atmosphere. Most abundant element of all. It is not. Okay, it is, they're talking about an earth crust, oceans. 46% by weight oxygen. Okay, in earth it is the most abundant element, but In universe it is not. In universe, hydrogen is the most abundant element. In human body and on earth, oxygen is the most abundant element, but whereas in the universe it is not. Earth crust, the most abundant element is oxygen, and human body also it is oxygen. In atmosphere as well, 21% constitutes oxygen itself. Group of calculations. Okay, the oxygen is the most abundant of all elements on earth. Oxygen forms about 46.6% by mass of earth's crust. Dry air contains 21% of oxygen by volume. However, the abundance of sulfur in the earth crust is only 0.03 to 0.1%. Oxygen's abundance is around 50%, but whereas copper is around at the highest of 0.1% in the earth's crust, which means oxygen is way more abundant than sulfur. And combined sulfur exists primarily as sulfates SO4, such as gypsum. Okay, gypsum. CaSO4 2H2O. 2H2O is the water of crystallization. And calcium sulfate. This is what we call gypsum. Epsom salt, which is magnesium sulfate and 7 water of crystallization. Barite, barium sulfate. These are naturally occurring minerals of sulfate or containing sulfate. And sulfides such as galena PbS, zinc blende, zinc sulfide basically, copper pyrites, CuFeS2. Both base we saw before it was existing with single metals like calcium, magnesium, barium and lead, even zinc, but in copper pyrites both copper and iron are mixed here. Traces of sulfur occur as hydrogen sulfide in volcanoes. We can also see hydrogen H2S in volcanoes, which is also a form of sulfur. And organic materials such as eggs, proteins, garlic, onion, mustard, hair and wool contain sulfur. Okay, abundance of oxygen is the most abundant with 46.6% earth crust, and dry air contains about 21%, and abundance of sulfur in the earth crust is only 0.03 to 0.1%. And some of the names of minerals of sulfur found in earth crust is gypsum, calcium sulfate, Epsom salt, magnesium sulfate, barite, barium sulfate, and sulfides of galena PbS, lead sulfide, and zinc blende, zinc sulfide, and copper pyrites, copper and iron sulfide, and found in volcanoes as H2S. Every organic material or most of the organic materials also contain sulfur. And the next two compounds of selenium and tellurium, where selenium is non-metal, tellurium is a metalloid, are also found as metaselenides and tellurides in sulfide ores. They are present in sulfide ores itself. Polonium occurs in nature as a decay product of thorium and uranium minerals. Basically, when uranium and thorium, these radioactive chemicals, undergo decay, polonium is formed. Polonium is a metal, and it doesn't exist as an individual element, but it is actually a decay of product of thorium and uranium minerals. Selenium and tellurium exist in sulfide ores. The important atomic and physical properties of group 16 along with configuration are given in table 7.6. Some of the atomic, physical and chemical properties and their trends are discussed below. Let's see the table first. 7.6 Some physical properties of group 16 elements. Atomic number of oxygen is 8, mass number is 16, configuration is helium 2s2 2p4, which is 1s2 is the helium configuration. Covalent radius is 66, ionic radius is 140, and electron gain enthalpy is the highest actually, which is highest. Ionization enthalpy is also the highest. Yes. But when we see in the nitrogens group, it is nowhere near, all these compounds are nowhere near the ionization enthalpy of the nitrogens, where it was really high compared to here. And in case of electronegativity, it is higher than nitrogen, having a 3.5, and that is why nitrogen oxides can exist, where nitrogen has a plus oxidation state. If oxygen was not more electronegative than nitrogen, those can't exist. Density, it is 1.32 C. Melting point is 55 Kelvin. Boiling point is 90 Kelvin. Oxidation states, it can be -2, -1, 1 and 2. Okay. Sulfur, it is 16, mass is 32, configuration is 3s2 3p4. All have a 3p or np4 configuration, ns2 np4 configuration. Covalent radius is significant increase from oxygen, ionic radius as well, and the least, sulfur has the least electron gain enthalpy of all the elements here, which is also not in by a very large margin. Ionization enthalpy, it is, we see decreasing down the group, which is normal. As for melting point, it is 393 Kelvin, and boiling point is around 718 Kelvin, which is actually very high compared to oxygen. Oxygen has the least boiling and melting points. Let's compare. 8, 16, 34, 52, 84 are the atomic numbers. And as for radius, covalent radius, as it should, increases down the group. As for ionic radius, it also increases down the group. Okay, and the electron gain enthalpy, it is somewhat different, and oxygen has the highest electron gain enthalpy, and the electron gain enthalpy from sulfur, it goes on increasing because this is a negative sign here. Oxygen has the highest, then sulfur to polonium, it continues to increase. It increases as we go down the group. And ionization enthalpy, it follows the trend, normal trend, where ionization enthalpy decreases down the group. Electronegativity also decreases down the group. Yes, electronegativity also decreases down the group, with polonium being a metal is the least electronegative, and tellurium is somewhat electronegative with a 2, but there is not much difference between sulfur and selenium because both are non-metals, but there is difference between oxygen and sulfur. That is why sulfates can exist. And melting point, it increases. Melting and boiling point, they increase as we go down the group, with oxygen having the least. Oxidation states, it is -2, -1, 1 and 2. 4 oxidation states for oxygen, and -2, 2, 4, 6 for sulfur, and -2, 2, 4, 6 exactly same for sulfur, selenium and tellurium. And polonium cannot exist as minus, and it can only donate electrons, with the oxidation states being 2, 4. Okay. Oxygen, okay. Next, I forgot the properties. Let's see the properties. Electronic configuration. The elements of group 16 have 6 electrons in the outermost shell, ns2 and np4, and have ns2 and np4 general configuration. Atomic and ionic radius due to increase in the number of shell. Atomic and ionic radius increase from top to bottom in the group. The size of oxygen atom is, however, exceptionally small. Ionization enthalpy decreases down the group. This is due to increase in size. Ionization enthalpy decreases down the group. Okay, this is normal. Increase in size, however, the elements of this group have lower ionization enthalpy. Yes, values compared to those of pnictogens in the corresponding periods. This is due to the fact that the group 15 elements have extra stable half-filled p orbital and electronic configuration. Electron gain enthalpy. Because of the compact nature of oxygen atom, it has less negative electron gain enthalpy than sulfur. Electron gain enthalpy, because of the compact nature of oxygen atom, it has less negative electron enthalpy than sulfur. Okay, it seems minus 144 is actually less ionization enthalpy, so we can say oxygen has the least ionization enthalpy and it decreases as we go down the group. However, from sulfur onwards, the value again becomes less negative up to polonium. Next is electronegativity. Next to fluorine, oxygen has the highest electronegativity value amongst the elements. Within the group, electronegativity decreases with an increase in atomic number. Within the group, as we go down the group, the electronegativity decreases. This implies that metallic character increases from oxygen to polonium. Let's see the example question. Elements of group 16 generally show lower values of first ionization enthalpy compared to corresponding periods of group 15. Why? We saw the exact answer before, because pnictogens have a half-filled configuration which is very stable due to exchange energy, and due to that the ionization enthalpy is more. That is the answer. Due to extra stable half-filled configuration, p orbitals configuration of 15 group elements, large amount of energy is required to remove electrons compared to group 16 elements. Physical properties. Some of the physical properties of group 16 elements are given in table 7.6. Oxygen and sulfur are non-metals. Selenium and tellurium and metalloids, whereas polonium is a metal. Wait. It seems they took selenium as a metalloid. But we can see that selenium is under non-metals, but it seems this is a new updated one, or this is an old one. Is selenium a metalloid or a non-metal? Selenium is generally classified as a non-metal, though it has some properties similar to metalloids. It's actually a non-metal, and this is also an updated periodic table where they took it as a non-metal, but the NCERT gave it as a metalloid, maybe because they consider it to be a metalloid because of its properties, or because it might be because it is outdated. Polonium is a radioactive and is short-lived. Half-life of 13.8 days. Okay, it is short-lived. All these elements exhibit allotropy. Wait. Yes, they show different forms. They exhibit different forms. The melting and boiling points increase with an increase in the atomic number. Basically, they are saying as we go down the group. The boiling and melting points will increase. The large difference between the melting and boiling points of oxygen and sulfur may be explained due to on the basis of their atomicity. Oxygen exists as a diatomic molecule, whereas sulfur exists as a polyatomic molecule. Basically, if we see the table, uh, melting point of oxygen is 55, whereas sulfur it is 400, and boiling point of oxygen is 90, and sulfur it is 700. This is a drastic increase compared to the slow increase as we go by here from sulfur to selenium. If we see, it is a slow increase from 400 to 490 and 700 to 950, but compared to that, from double digits to directly triple digits, here a jump. It is attributed to atomicity. Sulfur exists as S8 molecules, whereas oxygen exists as O2 molecules. Due to many forces of attraction, the boiling and melting points are increased. As for chemical properties, oxidation states and trends in chemical reactivity. Oxidation states for sulfur, selenium and tellurium are same, with being -2, 2, 4 and 6, -2, 2, 4 and 6, and -2, 2, 4 and 6. Basically, they can act as a electron taking group with a -2 oxidation state. Basically, they can form two covalent bonds accepting electrons, or they can themselves donate electrons, which can be 2, 4 or 6 electrons. This is exactly same in both sulfur, selenium and tellurium. Tellurium also shows the same thing, but in case of polonium, if we see, polonium has a 2, 4. It does not show +6 or -2 oxidation state, and in case of oxygen it does not have that many electrons to have a +6 configuration, or basically it doesn't use the ns2 electrons for bonding here, so it will have -2, -1 and +2. Okay. Let's continue with 16th group elements. Chemical properties of 16th group elements. The elements of 16th group exhibit a number of oxides, number of oxidation states. The stability of -2 oxidation state decreases down the group. As we see, polonium doesn't exhibit the -2 oxidation state. Polonium hardly shows -2 oxidation state. Since electronegativity of oxygen is very high, it shows only negative oxidation state as -2, except in case of oxygen fluoride, where its oxidation state is +2. Other elements of the group exhibit +2, +4 and +6 oxidation state, but +4 and +6 are more common in sulfur, selenium and tellurium, usually show +4 oxidation state. Okay, they are saying that +2 and in sulfur and selenium, tellurium, only +4, +6 oxidation states are common compared to +2. Selenium, tellurium and sulfur show +4 oxidation state in their compounds with oxygen and +6 with fluorine. They show +4 oxidation state with compounds with oxygen, sulfur, selenium and tellurium, and in case with fluorine they show +6. The stability of +6 oxidation state decreases down the group, and stability of +4 oxidation state increases, which is due to the inert pair effect, the inability of the NS2 electrons to bond. Bonding in +4 and +6 oxidation state is primarily covalent. In +4 and +6 it is mostly covalent bonds, and they are saying that +6 oxidation state stability decreases as we go down the group, and highest with being sulfur, and we see polonium doesn't show +6 due to inert pair effect, and oxygen can't show +6, and usually +4 is the most stable for sulfur, selenium and tellurium along with polonium, and +2 also loses stability as we go down. And here we see anomalous behavior of oxygen. In nitrogens we saw anomalous behavior of nitrogen. The anomalous behavior of oxygen, like other members of P block present in second period, is due to its small size, high electronegativity. One typical example of effects of small size and electronegativity is the presence of strong hydrogen bonding in H2O, which is not found in H2S. H2O is highly bonded, highly hydrogen bonding due to the high electronegativity of oxygen. The presence of d orbital in oxygen limits its covalency to 4. The absence of d orbitals in oxygen. All the second period elements mostly lack d orbitals, and this is why its covalency is reduced to or limited to 4, and in practice it rarely exceeds 2. Like, even though we say it has a covalence of 4, in nitrogen we saw it is exhibiting +3, +4 and +5 states, but in oxygen it mostly exhibits -2, -1, 1 and +2 states. On the other hand, in case of other elements of the group, the valence shells can be expanded and covalence exceeds 4. The first anomaly of oxygen is reactivity with hydrogen. All the elements of group 16 form hydrides of the type H2E. In case of nitrogen, we saw the oxides formed were EH3, but here it is H2E, where E is the chalcogen group. Some properties of hydrides are given in table 7.7. Let's see the table first. Properties of hydrides of group 16. The melting point is 273 Kelvin, 0 degrees for water, lesser for hydrogen sulfide, and even which is a little greater for selenium and more for tellurium. And they didn't give a polonium hydride. As for boiling point, water has a 100 degrees boiling point, which is 373 Kelvin. Sulfide has a significantly less boiling point, and we can say that water has the highest melting and boiling points, and melting and boiling points both increase. No, melting point increases as we go down the group. Okay, no, melting and boiling points increase as we go down the group, with an exception of water, which is H2O. And in case of the covalent radius or bond, the He bond, it is increasing as we go down the group, which is normal. The bond angle, which decreases as we go down the group because of the high size of the atom and more repulsions, I believe. And is the formation enthalpy. Water has the highest negative formation enthalpy, followed by sulfide, and it keeps on increases as we go down the group. And dissociation enthalpy or bond dissociation energy for water is 463, and it keeps decreasing as we go down the group. The dissociation constants are also given below. And let's see the reactivity of hydrogen. Their acidic character increases from H2O to H2 tellurium. As we go down the group, acidic character increases. The increase in acidic nature can be explained in terms of decrease in bond enthalpy for dissociation for He bond. We saw as we go down the group, the bond enthalpy is reducing, and as more ability to give out H plus ions, more the electronegativity of the atom or compound. In such a case, it is explained that as the bond enthalpy decreases as we go down the group, the acidic character also increases. Owing to the decrease in enthalpy for dissociation of He bond down the group, the thermal stability hydrates also decreases from H2O to H2PO. And due to the same reason, due to the decrease in dissociation enthalpy, bond dissociation enthalpy, the stability of the hydrates also increases as we go down the group. No, wait, the stability decreases as we go down the group. Easily the bond can be broken. Because of that, the stability is less as we go down the group. All the hydrate except water possess reducing property, and this character increases from H2S to H2T. As we go down the group, reducing character increases. Water doesn't have reducing ability, acting as a reducing agent. A reactivity with oxygen. All these elements form oxides of EO2 and EO3 types, where E can be sulfur, selenium, and tellurium or polonium. Ozone and sulfur dioxide are gases, while selenium dioxide is solid. Reducing property of dioxide decreases from SO2 to TeO2. What is reducing property here? Property in case of 16th group elements as we go down the group. 16th group elemental oxides actually. Reducing agent donates electrons, or substance strong red is more willing to lose electrons. Water doesn't want to lose electrons, but it seems sulfate can lose electrons to become +4 oxidation state. Okay, reducing, okay, I see. Because they undergo oxidation, they have a higher, as the ability to oxidize increases, the reducing power and acting as a reducing agent increases. All these elements forms oxides as EO2 and EO3 types, where E is sulfur, selenium, tellurium, or polonium. Ozone and sulfur dioxide are gases. Only sulfur dioxide and ozone are gases, while selenium dioxide is solid. And reducing property of these dioxide decreases from sulfur to tellurium. As we go down the group, the reducing property of these dioxides decreases. Reducing property means the ability to undergo oxidation. It decreases from sulfur to tellurium. Reducing property of as we go down the group, reducing character should decrease, but fine, I'll see it later. SO2 is reducing while TeO2 is an oxidizing agent. Besides EO2 type, sulfur, selenium and tellurium also form EO3 type oxides. SO3, SCO3 and TO3, both types of oxides are acidic in nature. Okay. Reducing property according to NCERT decreases as we go down the group, and ozone and sulfur dioxide are gases, whereas selenium dioxide is a solid, and there are EO3 types of solids, compounds. Reactivity towards halogens, elements of reactivity towards halogens. Elements of group 16 form a large number of halides of the type EX6, EX4 and EX2, where E is an element of the group X and element of the chalcogens, and X is the halogens. The stability of the halides decreases in the order of fluorine has the highest stability, and it decreases with chlorine, bromine and iodine, because these are already electronegative elements. Like the chalcogens are already electronegative elements, and halogens are even more electronegative elements. So electronegativity, due to this electronegativity, there is also decrease in stability. With fluorine being the highest electronegative, it can form compounds easily, and so fluorine also has a higher stability. Amongst hexahalides, means X6, EX6, hexafluorides are only stable halides. EX6 can only be formed by fluorides, which is actually stable. All hexafluorides are gaseous in nature. They are gaseous. They have an octahedral structure. Sulfur hexafluoride SF6 is exceptionally stable for steric reasons. Amongst the tetrafluorides, SO4 is a gas, SCF4 is a liquid, and TeF4 is solid. These fluorides have sp3 dehybridization and thus have a trigonal bipyramidal structure in which one of the equatorial positions is occupied by a lone pair of electrons. This geometry is also regarded as a seesaw geometry. The structure will be this is like a seesaw, where this is the two lone pair of electrons, which we can write it like this as well. This is like a seesaw structure where these are the X. This is a tetrafluoride or tetrahalide. The shape is seesaw, geometry is trigonal bipyramidal. All elements except oxygen form dichlorides and dibromides. Oxygen doesn't form dichlorides and dibromides. These dihalides are formed by sp3 hybridization and thus have tetrahedral structure. The well-known monohalides are dimeric in nature. Example S2F2, S2. Monohalides don't exist in single units like in case of dibromides and difluorides, like dibromide meaning for example, or dichloride meaning this is the +2 oxidation state for sulfur. But in case of monohalide, it exists as dimers. Here if we see S2Cl2, S2Br2, SCCl2, SC2Cl2, SC2Br2, these dimeric halides undergo disproportionation, where selenium SCCl2, SC2Cl2 will undergo disproportionation to give SCCl4 and 3SC, where the oxidation state in case of SC2Cl2 is +1, here it is 0, and here it is +4. Yes, it is +4. It is disproportionation reaction. Okay, the example here, H2S is less acidic than H2TE. Why? Sulfur is less acidic than H2TE because due to the decrease in bond dissociation enthalpy, as we go down the group, the bond dissociation enthalpy decreases, and less the bond dissociation enthalpy, less the stable the molecule, and easily donation of the H+ ions. Bond enthalpy down the group as the character increases. In text questions, list the important source of sulfur. Sulfur is found in the earth crust as sulfide ores, where it can exist as sulfates, calcium sulfate, magnesium sulfate. Calcium sulfate is called gypsum, magnesium sulfate is called something else, and it can also exist as other sulfate. It can also exist as sulfides, which we see ferrous sulfides, copper sulfides, and pyrites, which contain both copper and iron. And it also exists as zinc, lead sulfides. They have special names. This is in the earth crust, and it can also exist in many of the organic compounds or living cells, etc. Example, milk, hair, etc. Write the order of the thermal stability of hydrides of group 16 elements. Thermal stability of the hydrides of group 16 elements. Hydrides meaning H2O, H2S. As we the thermal stability, as I said before, the bond dissociation enthalpy decreases as we go down the group, so stability also decreases as we go down the group. So H2O has the highest stability, and polonium hydride has the least stability, and it decreases as we go down the group. Why is H2 a liquid and H2S a gas? Because of the high electronegativity. Maybe it is because of the high electronegativity of the oxygen atom, which will form high hydrogen bonding, which will lead to it being high molecular interaction or molecular attraction forces. This will lead to it being a liquid. And next, some of the important compounds with preparation of, starting off with dioxygen, which is O2. O2. Preparation. Diaction can be obtained in the laboratory by the following ways: by heating oxygen containing salts, such as this is in case of laboratory. There are three ways to obtain oxygen. We can heat salts such as chlorates, nitrates and permanganates, which contain oxygen. In case of chlorate, potassium chlorate here, which if we heat in presence of permanganate, MnO2, or manganate, that is magnesium dioxide, manganese dioxide. In presence of manganese dioxide, we heat potassium chlorate, we get potassium chloride and oxygen. By thermal decomposition of oxides of metals in the electrochemical series and higher oxides of some metals. Oxides of metals which decompose at high temperatures to give the metal and oxygen, which can be silver oxide giving us silver and oxygen, mercury oxide giving us mercury and oxygen, lead oxide giving lead and oxygen, and the same thing. The third way is hydrogen peroxide is readily decomposed in water and dioxygen by catalysts such as finely divided metals and manganese dioxide. Peroxide in water decomposes to give water and O2. On large scale, it can be prepared. These are three ways which we can prepare oxygen in case of a laboratory, which can be from chlorates, nitrates and permanganates, or which can be from thermal decomposition of metal oxides. And in the fourth preparation method, which is in the large scale or industry basis, it can be prepared from water or air, as air contains 21% oxygen and water contains one molecule, one atom of oxygen each molecule, H2O. Electrolysis of water leads to release of hydrogen at the cathode and oxygen at the anode. Industrially, dioxin is obtained from air by first removing carbon dioxide and water vapor and then the remaining gases are liquefied and fractionally distilled to give nitrogen and dioxygen, similar to preparation of dinitrogen. Properties of the dioxin are oxygen. Dioxin is a colorless and odorless gas. Its solubility in water is to the extent of 3.8 centimeter cube in 100 centimeter cube of water at 293 Kelvin. Nitrogen, we saw that ammonia, we saw that it was very insoluble in water, which is just sufficient for the vital support of marine and aquatic life. The organisms which live in water or in seas need oxygen, and they take the dissolved oxygen. So the dissolution rate or the extent of dissolution is 3.08 centimeter cube in 100 centimeter cube of water. This is at room temperature. It at 20 degrees Celsius, not room temperature. It liquefies at 90 Kelvin and freezes at 55 Kelvin. Oxygen atom has three stable isotopes of O16, 17 and O18. Nitrogen has 14 and 15. Molecular oxygen O2 is unique in being paramagnetic in spite of having even number of electrons. O2 is actually paramagnetic in nature, and even though it has even number of electrons. In the MOT we can see this. Molecular orbital theory. Dioxin directly reacts with nearly all metals and non-metals except some metals. Example, gold and platinum, which are the noble metals or inert metals, and some noble gases. It reacts with nearly all metals and meaning it reacts with most of the elements except gold and platinum and noble gases, some of the noble gases. Its combination with other elements is often strongly exothermic, which helps in sustaining the reaction. However, to initiate the reaction, some external heating is required, and bond dissociation for oxygen-oxygen double bond is high. The oxygen-oxygen double bond, which is a double bond, is high So even though the reaction with metals or other elements is exothermic, which is releasing energy, we need to provide energy to dissociate the oxygen double bond option. Some of the reactions of dioxin with metals, non-metals and other compounds are given below. As they said before, oxygen reacts with most of the elements. With calcium it gives quicklime, with aluminium it gives aluminium oxide, with phosphorus it gives P4O10, and with carbon it will give carbon dioxide, basically combustion of carbon, and zinc sulfide will with oxygen it will give sulfur dioxide and zinc oxide. With methane is combusted to give carbon dioxide and water. Some compounds are catalytically oxidized. For example, sulfur is oxidized with a catalyst of V2O5 to give SO3. Oxidation means addition of oxygen. HCl is oxidized to give CuCl2, in presence of CuCl2 to give water and chlorine. Uses or applications of oxygen. In addition to its importance in normal respiration and combustion processes, oxygen is used in oxyacetylene welding, in the manufacture of many metals, particularly steel. Oxygen cylinders are widely used in hospitals, high altitude flying and in mountaineering. The combustion of fuels, example hydrazines in liquid oxygen, provide tremendous thrusts in rockets. Basically acts as a kind of a combustion of fuels. Which of the following does not react with oxygen directly? Zinc will react, we saw the reaction with zinc. Titanium will react. Platinum doesn't react, iron doesn't react. Maybe platinum and titanium don't react with oxygen directly. Platinum is for sure it won't react with oxygen, but titanium I'm not too sure. Zinc, titanium and iron react directly with dioxygen. Yes, they all react except platinum. They all react directly. Complete the following reactions. C2H4 plus O2, basically a combustion of ethane, so it will give CO2 plus H2O. If we balance this, we will get C2H4, so 2 carbon, 2 hydrogen, 4 hydrogen, so total of 6 oxygen here, so 3 to the 6, 4, 6, oh, yes, balanced. C2H4 ethane will react with 3 oxygen molecules to give 2 CO2 plus 2 H2O, and 4 Al plus 3 O2 it will give Al2O3. Al2O3, 4 Al molecules, so 2 times this. Reaction is balanced. Now some simple oxides. A binary compound of oxygen with another element is called an oxide. Basically only 2 elements will react, that is called an oxide. A binary. As already stated, oxygen reacts with most of the elements of the periodic table. to form oxides. In many cases, one element forms two or more oxides. The oxides vary widely in nature and properties. Oxides can be simple, example magnesium oxide, aluminum oxide, or mixed like Pb3O4 and Fe3O4. Which, what does this mixed mean is, there is no compound as Fe3O4, and Fe3O4 is basically a mixture. Fe3O4 is basically a mixture of FeO, Fe2O3 and Fe FeO2. Oxides of iron. Yes, it is FeO. Basically, Fe3O4 is a mixture of FeO and Fe2O3. It does not. There is no compound of Fe3O4. I think it is given here. It's a mixed oxidation state, Fe2 plus and Fe3 plus, both FeO and Fe2O4. Color black, magnetic property, strongly magnetic. It is called magnetite. Here it is called ferric oxide, here it is called ferrous oxide. And there is also hydroxides here. And here the same case is for lead oxide as well. Simple oxides can be classified on the basis of their acidic, basic or amphoteric character. An oxide that combines with water to give an acid is termed as an acidic oxide. Basically, if the oxide will react with water to give an acid, it is called an acidic oxide. Example, SO2, Cl2O7, carbon dioxide, dinitrogen pentaoxide. The reaction is sulfur dioxide reacting with water to give sulfuric acid. As a general rule, only non-metal oxides are acidic, but oxides of some metals in high oxidation state also have acidic character. Mn2O7. In the Mn2O7, the oxidation state of magnesium is +7. At the +7 oxidation state, it can only accept electrons. It cannot donate electrons. Yes, it can only accept electrons, and accepting electrons is a acidic character. Because of such a reason, at high oxidation state, the metals will act as acids. Basically, only non-metal oxides are acidic in nature, but in some metals at high oxidation state, they also act as oxides. The oxides which give a base with water are known as basic oxides. Example, sodium oxide, calcium oxide, barium oxide. For example, calcium oxide quicklime combines with water to give calcium hydroxide, which is a basic reaction. In general, metallic oxides are basic, but some metallic oxide exhibit a dual behavior. They show characteristics of both acidic as well as basic oxide. It can also be acidic, as we saw here, but here it can show basic, mostly all show basic, but they can also show amphoteric. Such oxides are known as amphoteric oxides. They react with acids as well as alkalis. For example, Al2O3 reacts with acids as well as alkalis. Here aluminum oxide reacting with HCl to give water and salt as complex ion or a complex salt, and Al2O3 reacting with a strong base of alkali, NaOH, and water to give sodium acetate. No, it's a salt basically. There are some oxides which are neither acidic nor basics. Such oxides are known as neutral oxides. Example of neutral oxides are carbon monoxide, nitrogen monoxide, and Dinitrogen oxide, these are important to remember. Neutral oxides are carbon monoxide, nitrogen monoxide, and dinitrogen oxide. And the next compound we are going to study out is ozone, O3, which is an allotropic form of oxygen. Ozone is an allotropic form of oxygen. It is too reactive to remain for long in the atmosphere at sea level. When we see at sea level, it is so unstable that it will always react to form other compounds if it is at sea level. But at the height about 20 kilometers, it is formed from atmospheric oxygen in the presence of UV light. This ozone layer protects the Earth's surface from an excessive concentration of ultraviolet radiations. Preparation of the ozone: when a slow dry stream of oxygen is passed through a silent electrical discharge. Conversion of oxygen to ozone: 10% ozone. The product is known as ozonized oxygen, where we get 3O2 will become 2O3 at 298 Kelvin, and the formation or change in enthalpy, it will gain energy plus 143 kilojoule per mole. Since the formation of ozone from oxygen is an endothermic process, formation of ozone from oxygen is an endothermic process. It takes in energy. It is plus because it is taking this much amount of energy. It is necessary to use a silent electrical discharge in its preparation to prevent its decomposition. When we oxidize it at such high temperature, the energy required should be through a silent discharge, electrical discharge. Otherwise, the oxygen will directly take the energy and the oxygen-oxygen bond will dissociate. Concentration of ozone greater than 10% are required. This first preparation method is when if 100 molecules of O2, only 10% of these O2 will form ozone. If more than 10% is required, a battery of ozonizers can be used. And pure ozone, boiling point at slightly higher than water, a boiling point of 101.1 Kelvin can be condensed in a vessel surrounded by liquid oxygen. We need a battery of ozonizers which are used, and pure ozone, boiling point which is around 101 Kelvin, can be condensed in a vessel surrounded by liquid oxygen. Okay, liquid oxygen has a 90 Kelvin point. So properties: pure ozone is pale blue gas. It is slightly blue in color, dark blue liquid, and violet black solid. It is dark blue in liquid color, and it is violet and black in solid state. Ozone has a characteristic smell, and in small concentration it is harmless, but in large concentration it is poisonous or toxic. However, if the concentration rises above about 100 parts per million, which is 100 times 10 power minus 6 or 10 power minus 4 concentration in the atmosphere, breathing becomes uncomfortable, resulting in headache and nausea. Ozone is thermodynamically unstable with respect to oxygen, since its decomposition into oxygen results in liberation of heat. Delta H is negative, and it increases its entropy, because more energy, more kinetic energy as well, and change in entropy is positive as delta P increases. These two effects reinforce each other, resulting in large negative Gibbs energy change, delta G, for its conversion into oxygen. It is not really subsidizing, therefore high concentration of ozone can be dangerously explosive. Due to the ease with which it liberates atoms of nascent oxygen, O3 will give O2 plus O. It acts as a powerful oxidizing agent. For example, it oxidizes lead sulfide to lead sulfate and iodide ions to iodine. PbS plus 4O3 will give us lead sulfate plus oxygen, and iodide ions with water, and ozone will give us iodine solid, oxygen, and hydroxide ions. When ozone reacts with an excess of potassium iodide solution buffered with a borate buffer, pH of 9.2, iodine is liberated, which can be titrated against a standard solution of sodium thiosulfate. This is a estimating O3 gas. Okay, let's see the properties again. Ozone is pale blue as a gas, dark blue as a liquid, and violet black as a solid. It has a characteristic smell, and at small concentration it is harmless, and it is explosive because as ozone has a high tendency to dissociate and form oxygen, and in this liberation the energy is exothermic and energy is released. This energy will increase the entropy, which will increase the kinetic energy of the molecules and increase the randomness of the molecules, and this will result in a large negative energy change. Because of that, it is explosive. This rapid decomposition can lead to high energy release, which can be explosive, and it has a high oxidation capacity because ozone can liberate nascent oxygen, which will be able to oxidize things or substances. Lead sulfide reacting with ozone will give lead sulfate and oxygen, and iodide ions reacting with water and ozone will give hydroxide and I2 plus O2. When ozone reacts with excess amount of Ki solution buffered with a borate, okay, iodine is liberated, which can be titrated against a standard solution of sodium thiosulfate. They're basically giving a method for us to estimate the O3 gas, quantitative, how much O3 gas is there. We can estimate based on how much iodide it is liberating. Based on how much iodide, based on this reaction, we saw that iodine is reacting with ozone to give iodide. If we titrate against it, we will get the how much the quantity of O3 is. Quantitative method for estimating O3 gas. Experiments have shown that nitrogen oxides, particularly nitric oxide, okay, combines very rapidly with ozone. Thus, the possibility that nitrogen oxides emitted from the exhaust system of supersonic jet airplanes might be slowly depleting the concentration of ozone layers in the upper atmosphere. Basically, they are saying how one of the causes for the ozone layer depletion, which may be due to nitric oxide, which react very easily with or very rapidly with the ozone to give nitrogen dioxide and oxygen. This reaction will therefore deplete the ozone layer. One more threat to this ozone layer is probably posed by the use of freons, basically CFCs. CFCs is what we call freons, chlorofluorocarbons, which are used in aerosol sprays and as refrigerants. Freons, CFCs. Another names of CFCs is freons. This is the resonance structure of oxygen. There are two canonical structures or resonance structures, and ozone actually exists in a hybrid of these two structures, which are used in aerosol sprays and as refrigerants. The two oxygen-oxygen bond lengths in the ozone are around 128 picometer and are identical, and the molecule is an angular, meaning it is bend shaped with a bond angle of about 170 degrees. It is not 170 but 170 degrees. It is a resonance hybrid of two main forms. It is used as a germicides. Maybe it's due to the hyperreactivity of the ozone molecule. It will react with germs to kill them. disinfectant and for sterilizing water. Okay, it is also used for bleaching oils. Ivory, this is mainly due to the highly reactive nature or oxidizing property of the, what we call it, yeah, ozone. Flour, starch, etc. It acts as an oxidizing agent in the manufacture of potassium permanganate. Oxidizing potassium permanganate is KMnO4. So yes, it acts as an oxidizing agent. Why does O3 act as a powerful oxidizing agent? It acts as a powerful oxidizing agent because it can dissociate easily with an endothermic reaction to give energy as well as a nascent oxygen. And how is O3 estimated quantitatively? When reacted with excessive potassium iodide and in presence of a borate buffer, and when we titrate the iodide ions, we will get the quantitative estimation of how much ozone is there. And then next is sulfur, the allotropic form. We saw that oxygen doesn't show allotropic forms and sulfur does. As nitrogen doesn't show allotropic forms, oxygen also doesn't show allotropic forms, but as phosphorus, sulfur also shows allotropic forms. Sulfur forms numerous allotropes, of which the yellow rhombic alpha sulfur and the monoclinic beta sulfur forms are the most important. In phosphorus, we studied three forms of the red, the white, red, and black. Here we are studying about the two structures, alpha and beta sulfur, where alpha is also called the yellow rhombic sulfur, or beta is called the monoclinic sulfur. These are which we are going to study about, and these are not all the forms of sulfur. The stable form at room temperature is the rhombic sulfur, meaning alpha sulfur, yellow rhombic sulfur, which transformed to monoclinic sulfur when heated above 369 Kelvin. Both create each other, like how white phosphorus forms red and red phosphorus forms black, or white phosphorus directly forms black phosphorus. In the same way, yellow rhombic sulfur or alpha sulfur will react, at room temperature it is stable. Alpha sulfur is stable at room temperature, but it transforms into beta sulfur, monoclinic sulfur, at temperatures above 369 Kelvin, when it is heated above 369 Kelvin. Rhombic sulfur, alpha sulfur, yellow rhombic sulfur. This allotrope is yellow in color, that is why we call it as yellow rhombic sulfur. Melting point is 385.8 Kelvin and specific gravity 2.06. Rhombic sulfur crystals are formed on evaporating the solution. The melting point is kind of high. I don't know what specific gravity means. They gave something similar for phosphorus as well, or in the nitrogen's group, which is around 1.5 or 1.05. Rhombic sulfur crystals, allotrope is yellow in color. Okay, rhombic sulfur crystals are formed on evaporating the solution. If we heat or completely vaporize the solution contain this rhombic or alpha sulfur, we will get rhombic sulfur crystals, rhombus shaped sulfur crystals. On roll sulfur in CS2. This solution is not water solution but a solution of the CS2. It is insoluble in water but dissolves to some extent in benzene, alcohol and ether. It is completely soluble in CS2. It is readily soluble in CS2. And next is beta sulfur, monoclinic sulfur, which is found above 369 Kelvin if we heat the alpha sulfur. Its melting point is around 393 Kelvin and specific gravity is 1.9, which is what it means I don't know, but it is extremely close to the alpha sulfur. What does it mean to say that the specific gravity of alpha sulfur is 2.06 and 1.98 for beta sulfur or for monoclinic sulfur. This is also alpha sulfur or rhombic sulfur. What is specific gravity? Specific gravity is the ratio of density of substance to the density of water. Relative density. Specific gravity for solids and liquid. It is 2.06. What does this mean? It means that is denser than, how much times it is denser than monoclinic sulfur? Okay, both are heavier than water, so they sink in water. Structural reason, how sulfur atoms are arranged, more tightly packed. As density increases, it's based on structure. Less dense monoclinic structure, even though both are made of S8 rings. The rhombic structure or rhombus structure is formed due to S8 rings. Their crystal packing differs, which affects how tightly. Okay, summary: alpha sulfur. Is this relative? Can this also be called relative density? Which is our normal relative density. It seems to be the case. So let's go next. Monoclinic sulfur, it is also soluble in CS2 solution. This forms a sulfur is prepared by melting rhombic sulfur in a dish and cooling till crust is formed. Two holes are formed in the crust and the remaining liquid poured out. On removing the crust, colorless needle-shaped crystals of beta sulfur are formed. It is stable above 369 Kelvin temperature and transforms into alpha sulfur below it. Conversely, alpha sulfur is stable below 369 and transforms into beta sulfur above this. But they gave the boiling point of the alpha sulfur to be around melting point of alpha sulfur to be around 385. If it is not stable, maybe they forced it to be stable to find such a temperature and its melting point. At 369 Kelvin, both the forms are stable. This temperature is called transition temperature. The temperature of 369 Kelvin is called transition temperature, where both alpha and beta forms can coexist. But below 369 Kelvin, only alpha sulfur can exist, and above 369, only beta sulfur. Both rhombic and monoclinic sulfur have S8 molecules. These S8 molecules are packed to give different crystal structures. The S8 ring is both the forms in pugged and has a crown shaped. The molecular dimensions are given in figure 7.5a. A is the alpha sulfur and B is the beta sulfur, meaning monoclinic sulfur. Here it is also S8 molecule. It seems like a crown shaped here. Here it seems like a lightning symbol. And the bond length also seems to be same for both the molecules. Approximately there is only a 1.7 picometer difference, but the bond angle variation is comparatively higher, with the alpha having 107 degrees and the beta one having 102.2 degrees. There is a slight increase in bond length and slight decrease in bond angle as we go from alpha to beta. Both are S8, meaning both the alpha and beta allotropes have 8 sulfur atoms. 1, 2, 3, 4, 5, 6, 7, 8. 1 2 3 4 5 6. Wait, I think they did not complete this structure. Wait, no, this is the S6 form, not the beta form. This is not the this is not the beta form. This is the S6 form. And several other modifications of sulfur containing 6 to 20 sulfur atoms per ring have been synthesized in the last 2 decades. This is just a sample but other containing even 20 sulfur atoms per ring are also created or synthesized. But the stability doesn't mean they can be stable at every temperature. In cyclo S6, this lightning symbol shaped structure, the ring adopts the chair form, or we can say the chair as well. The molecular dimensions are as shown in figure 7.5b. At elevated temperature 1000 Kelvin, S2 is dominant species and is paramagnetic like O2. S2 can be found. Normally we see S8 structures, but S2 can be found at 1000 Kelvin temperature, where it is paramagnetic in nature like O2. Which form of sulfur shows paramagnetic behavior? In vapor state, sulfur partly exists as S2 molecule which has 2 unpaired electrons in the anti-bonding pi star orbitals like O2, and hence it is exhibiting paramagnetism. The answer is just here. And the next is sulfur dioxide preparation, which is a compound of sulfur. Preparation: sulfur dioxide SO2 is formed together with little 6 to 8% sulfur trioxide when sulfur is burnt in air or oxygen. This sulfur dioxide is found is not completely pure, and it contains 6 to 8% of sulfur trioxide as well, plus six to 8% of sulfur trioxide. In the laboratory, it is readily generated by treating a sulfite SO3 minus with dilute sulfuric acid. Basically, a salt containing a sulfite salt is reacted with H2SO4, which is sulfuric acid, to give us water and SO2 gas. Industrially, in large scales, it is produced as a byproduct of roasting of sulfide ores. If we roast iron ores or any kind of sulfide ores in presence of oxygen or open to atmosphere, we can say, we will get ferric oxide and sulfur dioxide gas. This gas, after drying it, liquefied under pressure and is stored in steel cylinders. After drying, this gas is liquefied, turned into liquid and under pressure and is stored in steel cylinders. It is a byproduct, but this is as it has uses. It is stored. Properties: sulfur dioxide, they only give about 3 preparation methods. One is burning sulfur, which has impurities. Second, it is through sulfide salts. Third, industrially as a byproduct of, this is actually I think metallurgy, right? Yes, yes, it is a byproduct of metallurgy, which can be extraction, or which is a process under metallurgy, which we have studied under in lower classes. Properties: sulfur dioxide is a colorless gas with a pungent smell and is highly soluble in water. NH3 was also a pungent gas. It's also colorless, but NH3, unlike here, is highly insoluble in water. Wait. I think it is soluble in water. Actually, yeah, it is soluble in water because of the nitrogen and nitrogen electronegativity forming bonds. Yes, it is highly soluble in water. As similar to NH3, sulfur dioxide is also colorless, has a pungent smell, and is also highly soluble in water. It liquefies at room temperature under pressure of 2 atmosphere and boils at a pressure. If it liquefies at room temperature, even if it's under a pressure of 2 atmospheres, it is considerably less melting, boiling point. Sulfur dioxide, it has a high boiling point actually. It has a 263 Kelvin boiling point. But because of the 2 atmosphere pressure under even at room temperature, it can get liquefied. Sulfur dioxide, when passed through water, forms a solution of sulfurous acid. It is not H2SO4 but H2SO3. SO2 plus water will give H2SO3. It reacts with sodium hydroxide solution forming sodium sulfide, which then reacts with more sulfur dioxide to form sodium hydrogen sulfide. NaOH reacting with sulfur dioxide to give sodium sulfide plus water. This sodium sulfide will react with more sodium dioxide to give sodium hydrogen sulfide. In its reaction with water and alkalis, the behavior of sulfur dioxide is very similar to that of carbon dioxide. Reaction with water and alkalis, as how carbon dioxide reacts with water and alkali, this sulfur dioxide also behaves similar way. Even though the carbon family and this family is one group apart, the basic properties are similar. One group and one period apart. Sulfur dioxide reacts with chlorine in the presence of charcoal. Reacts with chlorine in the presence of charcoal, which acts as a catalyst. Sulfur dioxide reaction with chlorine to give sulfuryl chloride, SO2Cl2. If it was SOCl2, I would call it thionyl chloride, but it is sulfuryl chloride because SO2Cl2. It is oxidized to sulfur trioxide by oxidation in the presence of vanadium 5 oxide. Basically, the reaction is a two-step reaction with sulfur dioxide first reacting with chlorine in presence of a charcoal catalyst to give sulfuryl chloride, and sulfur dioxide again reacting with oxygen to give, in presence of vanadium oxide, to give vanadium 5 oxide to give the sulfide gas. When moist, SO3 gas. When moist, sulfur trioxide gas. When moist, sulfur dioxide behaves as a reducing agent. Moist sulfur dioxide behaves as a reducing agent. For example, it converts iron 3 to iron 2. It helps in reduction, so it undergoes oxidation and decolorizes acidified potassium permanganate 7 solution. The latter reaction is a convenient test for the gas. Okay, there is a test given here. The test is basically potassium permanganate solution. It decolorizes the potassium permanganate solution. If SO2, moist SO2 reacts with potassium acidified potassium permanganate solution, it decolorizes or changes the color of the solution. This can act as a test. The first reaction is reducing agent, acting as a reducing agent. Fe3 plus SO2 plus water will reduce iron from Fe3 plus to Fe2 plus sulfate and 4 H plus ions are produced, and as a test 5 SO2 permanganate water will give sulfate H 4H plus and Mn2 plus. This is because MnO4 minus is turning into 2Mn plus because it's an acidified medium. This is the resonance structures of SO2. The molecule of SO2 is angular, bend shaped. It is resonant hybrid of two canonical structures. Uses of sulfur dioxide. Why we store the sulfur dioxide, which preparation method we saw from the byproduct of metallurgy, where ferrous sulfide ore is roasted to give ferric oxide and or ferrous oxide and sulfur dioxide. This sulfur dioxide is liquefied, dried and liquefied and stored in metal cans or bottles or something. Uses: sulfur dioxide is used 1 in refining petroleum and sugar, in bleaching wool and silk, as an anti-chlor, meaning against chlorine, disinfectant and preservative, sulfuric acid, sodium hydrogen sulfide and calcium hydrogen sulfide. Industrial chemicals are manufactured from sulfur dioxide. These chemicals can be manufactured from sulfur dioxide. Liquid SO2, liquid sulfur dioxide, is used as a solvent dissolved number of organic and inorganic chemicals. What happens when, in text question, what happens when sulfur dioxide is passed through an aqueous solution of Fe3 salt? When an aqueous solution means sulfur dioxide is moist and it will reduce Fe3 plus to Fe2 plus. This is acting as a reducing agent. Basically this reaction. That is the answer to the first in-text question. Comment on the nature of two SO bonds formed in SO2 molecule. Are the two bonds in this molecule equal? Yes, they are. It exists in two canonical structures here given here, which is kind of similar to O3 molecule, but in case of 1O there is a sulfur molecule here. I believe they are equal in bond length because they don't exist like this. They exist as a hybridized structure and not these individual resonance structures. Because of that, the bond length, the SO bond length will be equal, as in case of oxygen ozone we saw it was around 128 or something. Here also there should be a fixed bond length. In SO2 molecule is the bond length of SO bonds equal? Yes, it is equal. Let's see why. Because the resonance structures, it's actually a hybrid structure. Because of that, the intermediate of the hybrid structure will have equal bond lengths. Next is oxoacids of sulfur. Sulfur forms a number of oxoacids such as H2SO4, H2S2O3, H2S2O4, H2S2O5, H2SXO6, where X can be from 2 to 5, H2SO4, H2S2, whatever. Some of these acids are unstable and cannot be isolated. They are known in aqueous solutions or in form of their salts. Structures of some important oxoacids are shown in the figure 7.6. important oxoacid, sulfurous acid, H2SO3. In place of there's one S and O bond and two S OH bonds. And H2SO4, there is a lone pair in case of H2SO3, but this lone pair is filled here in H2SO4. And in case of peroxydisulfuric acid, peroxy meaning there is an OO bond, so because of that it is extremely similar to the oxidation state here, it is +6. For sulfur the oxidation state is -2, -2, -1, -1. So it is, yes, it is +6 for sulfur in here in this molecule, in the peroxysulfuric acid. In case of here it is -2, -2, -1 and -1. So here as well the oxidation state is +6, and in case of here it is -2, -1 and -1. So it is oxidation state of sulfur. In the sulfurous acid it is +4. In sulfuric acid, peroxodisulfuric acid, it is +6 oxidation state. In case of here it is an SOS bond, -2, -2, -1 and -1. Here as well the oxidation state is +6. Okay, one of the important compounds here, we do not study too deeply about the oxoacids like in case of nitrogen or phosphorus. Here they just gave some compounds and their structures, and basically they said that all of these they gave examples of do not exist stably, and we cannot isolate them like in case of sulfuric acid, and we can only see them in ions, in aqueous form as ions or as salts. And the compound which we are going to study about now is sulfuric acid. Manufacture of sulfuric acid is one of the most important industrial chemicals worldwide. Sulfuric acid is manufactured by the contact process, which involves 3 steps. We studied about 3 processes of the Haber's process for preparation of ammonia, Ostwald's process, preparation of nitric acid, which is nitrogen monoxide reacting with water to give something which was, yes, the Ostwald's process is ammonia reacting with oxygen and in presence of platinum, 500 Kelvin temperature, 9 bar of pressure and RT gauge catalyst, giving nitrogen monoxide and water. This nitrogen monoxide will react with oxygen to give nitrogen dioxide. This nitrogen dioxide will dissolve in water to give our nitric acid. This is called the Ostwald process, a 3-step process. The third process which we are going to study about is the, what is it? It is a contact process, and we study about 2 tests, one being the brown ring test, which is, I think, of nitric acid itself. Nitric acid. Yes, the brown ring test of the nitric acid, where the NO3 minus ion will react with iron and H plus to give, where the ion is oxidized, and this oxidized ion will form a complex. This will form a brown complex, to give us the bounding test. And the next is from sulfur. No, not sulfur. It is from. It is not a named test. Actually, convenience process of a test. Yes, this test for sulfur dioxide, where it reacts with potassium permanganate and oxy Okay. Sulfuric acid. Manufacture of sulfuric acid is one of the most important industrial chemical worldwide, and sulfuric acid is manufactured by the contact process, which involves three-step burning of sulfur or sulfide ores in air to generate SO2, conversion of SO2 to SO3 by reaction with oxygen in the presence of catalyst V2O5, basically reactions of preparation of SO2 and reactions of SO2 here. SO2 plus O2 gives 2SO3, and absorption of SO3 in H2SO4 to give oleum. Wait. To give oleum H2SO2 SO7. A flow diagram for the manufacture of sulfuric acid is shown in 7.7. Sulfuric acid manufacture. Okay, I'll just read the paragraph once before. The SO2 produced is purified by removing dust and other impurities such as arsenic compounds. This SO2 is produced by burning of sulfur or sulfide ores. And the key step in manufacture of H2SO4 is the catalytic oxidation of SO2 with O2, which gives SO3 sulfur trioxide in the presence of vanadium pentoxide, and vanadium is acting as a catalyst. Vanadium oxide is acting as a catalyst, and 2SO2 plus O2 gives SO3. This has a reaction enthalpy of minus 196.6 kilojoule per mole. The reaction is exothermic, that is why it is negative. Reversible, and the forward reaction leads to decrease in volume. Therefore, low temperature and high pressure are favorable conditions for maximum yield of SO3, but the temperature should not be very low, otherwise rate of reaction will become slow. Because it's an endothermic process, there should be low temperature and high pressure. But the temperature should not be very low, otherwise the rate of reaction will become slow. In practice, the plant is operated at the pressure of 2 bar and a temperature of 720 Kelvin. The SO3 gas from the catalytic converter absorbed in concentrated H2SO4 to produce oleum. Dilution of oleum with water gives H2SO4 of the desired concentration. In the industry, two steps are carried out simultaneously to make a process continuous one and also to reduce the cost. Okay. This is actually involved also in giving desired concentration of H2SO4 depending on how much water we dissolve. SO3 plus H2SO4 gives oleum. The sulfuric acid obtained by contact process is 96 to 98% pure. This is a flow chart. Sulfur will burn in air to give sulfide ores, or sulfur will burn in oxygen to give SO2 plus oxygen. This is passed through a dust filter or a precipitator, and then it is gone through a water spray where it is washed and cooling tower. Then it is gone to the drying tower where concentrated H2SO4 is sprayed. It is dried up, and this dried SO2 plus O2, the sprayed concentrated H2SO4 is actually very less amount, I believe, for this process to be efficient. And this dry SO2 and this concentrated H2SO4 is solely acting as a dehydrating agent, and this dried SO2 plus oxygen gas will go to an arsenic purifier containing gelatinous hydrated ferric oxide, which will remove all other impurities and a preheater, and this contains vanadium hydroxide, I mean pentaoxide, vanadium pentaoxide, which will convert this SO2 and oxygen to react to form SO3. This SO3 is again sprayed with concentrated sulfuric acid in presence of quartz to give oleum, which if we dissolve or dilute with water will give us H2SO4 of our desired concentration. This is what we call contact process. The catalyst in contact process, we can say it is vanadium pentaoxide or V2O5. Properties: sulfuric acid is a colorless, dense, oily liquid. Sulfuric acid is a colorless, dense, oily liquid with a specific gravity of 1.84, which is density, relative density at 298 Kelvin. The acid freezes at 283 Kelvin and boils at 611 Kelvin. It dissolves in water with the evaluation of large quantity of heat. It is basically an exothermic reaction. Hence, care must be taken while preparing sulfuric acid solution from concentrated, basically dilution. When we are diluting, large amount of heat will be released, so it should be taken very carefully. It should be done very carefully. Concentrated acid must be added slowly into the water with constant stirring. And we do not add water to the acid, but acid to the water. The chemical reactions of sulfuric acid are as a result of the following characteristics. Why sulfuric acid reacts is because low volatility, it can't turn into vapors, because as we saw here, the boiling point is at 611 Kelvin, very high boiling point. It has strong acidic character, which can easily liberate H plus ions, strong affinity for water, and ability to act as an oxidizing agent. It acts as an oxidizing agent in aqueous solution. Sulfuric acid ionizes in two steps. H2SO4 plus H2O gives hydronium ion and HSO4 minus. This is the first step. This is the equilibrium constant. It's very large, larger than 10, meaning the equilibrium constant is the concentration of products whole to the power of coefficients by reactant, product of reactant concentrations. If it is really greater, the equilibrium constant is really high, which they say is greater than 10, that means in the first step the product is almost instantly formed. If this is, the product concentration must be really high. Because of such a reason, this step is very fast. And the second step is HSO4 minus will react with water to give H3O plus and SO4 2 minus. This is as we saw here, where it was about 10. Here it was 1.2 into 10 power minus 2. The larger value of Ka1, step 1, greater than 10 means that H2SO4 is largely dissociated into H plus and HSO4 minus ions. Greater the value of dissociation constant, the stronger, okay, this is not the dissociation, equilibrium constant, it's the dissociation constant. The acid forms two series of salts, normal sulfates such as sodium sulfate and copper sulfate, and acid sulfates, sodium hydrogen sulfate is an acid sulfate. Sulfuric acid, because of its low volatility, can be used to manufacture more volatile acid from their corresponding salts. Example, metal halide plus H2SO4 will give hydrogen halide plus metal sulfate. This X can be fluorine, chlorine, or NO3 group. Concentrated sulfuric acid is a strong dehydrating agent. Many wet gases can be dried by passing them through sulfuric acid. That is what happened in the contact process as well, where the first thing happened was sulfur dioxide is avoided from sulfides or sulfur burning, and this sulfur dioxide is then purified or filtered, then reacted in the presence of vanadium oxide to form, what was it? Yes, sulfur trioxide plus sulfur trioxide, which gives which this sulfur trioxide will again react with concentrated H2SO4, which will give oleum. Concentrated sulfuric acid is a strong dehydrating agent. Many wet gases can be dried by passing them through sulfuric acid, provided the gas do not react with the acid. Sulfuric acid removes water from organic compounds. It is evident by its charring action on carbohydrates, where this sucrose reacting with H2SO4 will turn into carbon and H2O. Hot concentrated sulfuric acid is moderately strong oxidizing agent. In this respect, it is intermediate between phosphoric and nitric acid. I believe phosphoric and nitric acids are more oxidizing agent. Both metals and non-metals are oxidized by concentrated sulfuric acid, which is reduced to SO2. Cu plus 2H2SO4 concentration. Reactions of H2SO4, we will get copper sulfate and sulfur dioxide plus water. Sulfur plus H2SO4 will give us 3 sulfur dioxide and water. Carbon plus H2SO4 will give us CO2, 2SO2 and water. Sulfuric acid is very important industrial chemical, and nation's industrial strength can be judged by the quantity of sulfuric acid it produces and consumes. It is needed for the manufacture of hundreds of other compounds and also in many industrial processes. The bulk of sulfuric acid produced is used in the manufacture of fertilizers. Bulk of sulfuric acid produced is used in the manufacture of fertilizers. The bulk of sulfuric acid is used in the manufacture of fertilizers. Okay, ammonium sulfate, superphosphate. Other uses are in petroleum refining, manufacture of pigments, paints, dyestuff intermediates, detergent industry, metallurgical applications, example cleansing metals before enameling, electroplating and galvanizing, storage batteries, manufacture of nitrocellulose products as a laboratory reagent. Due to this many uses, as higher the industrial strength, more the products we produce. So most of these products require HCl. I mean not HCl, H2SO4. So as more the H2SO4 we produce, the more the industrial strength of the nation. The example box is empty. Fine. Mention the 3 areas in which H2SO4 plays an important role. 3 areas. Here all the uses are mentioned. Petroleum refining, in manufacture of processes, fertilizers, manufacture of pigments, paints and dyestuff, detergent industry, metallurgical applications, manufacture of cellulose, nitrocellulose products, laboratory reagent, etc. This is the applications of H2SO4. Write the conditions to maximize the yield of H2SO4 by contact process. By contact process, the yield of H2SO4 is maximized by, I think, let's see again. The sulfur is 96% pure. Let's read the column again. Manufacture sulfuric acid is one of the most important industrial chemicals worldwide. Sulfuric acid is manufactured by contact process, which involves 3 steps: burning of sulfur or sulfide ores in air to generate SO2, conversion of SO2 to SO3 by the reaction of oxygen in the presence of a catalyst vanadium, and absorption of SO3 in H2SO4 to give oleum H2SO4 or H2SO4 The SO2 produced is purified by dust and other impurities. The key step in manufacture of H2SO4 is catalytic oxidation of SO2 with O2 to give SO3 in the presence of vanadium catalyst. The reaction is exothermic, reversible, and forward reaction leads to decrease. And therefore, yes, for maximum yield, low temperature and high pressure is required, but the temperature should not be very low, so otherwise the rate of reaction will become even more slow. In practice, the plant is observed at a pressure of 2 bar and a temperature of 720 Kelvin. 2 bar pressure and 720 Kelvin of temperature. Basically, the conditions required are low temperature and a high pressure, where temperature is standard of 720 Kelvin and the pressure is 2 bar. Why is Ka2 much greater for H2SO4 in water? The first step reaction, it is much greater, maybe because they didn't give the reason, right? They didn't give the reason. Means that had largely associated greater values. Let's see answer here. Why is K wait question is much smaller than the first one when dissociated. Here's the key idea. Sulfuric acid is a diprotic acid, which means it can give 2 protons. First dissociation is very strong. This step is essentially completed in water. Is considered a strong acid at its first step. Very large, approaches infinity. Second dissociation weaker, HSO4 minus. It will give H plus and HSO2 minus. And this is a reversible weak acid. So why that is the case? Electrostatic repulsion. After one electron, it is negatively charged and it attracts the H plus. It is due to loss of stability. And this molecule HSO4 minus is already stable, but taking electron might really decrease the stability. Water stabilizes ion, but it does so better when the dissociation is more favorable energetically. In water, second proton dissociation is not very favorable energetically. Like more energy is required to reduce the stability. So because of that, the first dissociation constant is very higher than the second dissociation constant. Basically stability. In chemistry, everything can be answered by stability. At least mostly. And with this we complete the 16th group elements, and coming to the 17th group elements of halogens, we can see the periodic table for halogens. Oxygen, the 15th group contained nitrogen, phosphorus, arsenic, antimony and bismuth. The 16th group contained oxygen, sulfur, tellurium, selenium and polonium, and the 17th group will contain fluorine, chlorine, bromine, iodine, astatine and tennessine. Tennessine, which we are not going to study. Basically, excluding tennessine, all the 17th group elements are non-metals. Fluorine, chlorine, bromine, iodine and astatine all being non-metals. So let's see. Group 17 elements. Fluorine, chlorine, bromine, iodine, and astatine are members of the group 17. These are collectively known as halogens. Greek halo meaning salt and genes meaning bond, which means salt producers, because NaCl is a salt. Halogens are highly reactive, non-metallic elements. They are reactive and they are non-metals. Like group 1 and group 2, the elements of group 17 show great similarity amongst themselves. That is why hydrogen, acting as both a group 1 or group 2 element, like taking electrons, giving electrons easily, and it also acts as a halogen accepting electrons. Because of that is the reason why there was a problem in deciding the position of hydrogen. They did place it here, but it was hard to distinguish if you should place hydrogen in the alkali group or in the halogen group, because it has similar properties of both alkali and the halogen groups. Halogen also is very reactive, alkali also very reactive, but here it is non-metal, here it is metal. The elements of group 17 show great similarity amongst themselves. That much similarity is not found in the elements of other groups of the periodic table. We saw that all the elements of the 17th group are metals except non-metals except tennessine. Also, there is a regular gradation in their physical and chemical properties. Astatine is a radioactive element. The occurrence, first topic being occurrence. Fluorine and chlorine are fairly abundant, while bromine and iodine are less so. Fluorine is present mainly as insoluble fluorides, fluorspar, strange name, CaF2, and cryolite, Na3AlF6, and fluorapatite. And we studied about the apatite family, where in the nitrogens group, apatite family being calcium salts, calcium phosphorus salts, apatite family. So here it is fluorapatite. There also we saw the same exact example of the fluorapatite, Ca3PO42 and CaF2, and small quantities are present in soil, river water plants, and bones and teeth of animals. Calcium carbonate is also, not calcium carbonate. Seawater contains chlorides, bromides, and iodides of sodium, potassium, magnesium, and calcium, but is mainly sodium chloride solution, 2.5% by mass. The deposits of dried up seas contain these compounds. Example: sodium chloride, carnallite, KCl, MgCl2, 6H2O. Carnallite is a double salt, I don't remember, but it was there in complex compounds, coordination compounds. Certain forms of marine life contain iodine in their systems. Marine life contain iodine in the system. Various seaweeds, for example, contain up to 0.5% of iodine, and saltpeter contains up to 0.2% of sodium iodide. Child saltpeter is sodium nitrate. Basically, this is also in the first page itself, it was there of this chapter. Child saltpeter, sodium nitrate, and Indian saltpeter, potassium nitrate, NaNO3, and NaNO3 is child saltpeter, and KNO3 is Indian saltpeter. And this child saltpeter also contains up to 0.2% of sodium iodate. Iodate meaning, I think, IO3 minus. The important atomic and physical properties of group 17 elements along with their electronic configuration are given in table 7.8. These are the places which we find the halogens. When we see in other two groups where 15 pnictogens and chalcogens, we say that we only studied deeply about first two elements, oxygen and sulfur, and nitrogen and phosphorus. These were the most abundant, and the remaining elements were not so. But here we see all are not so abundant, but in somewhat okay quantities here. And here they give the properties, atomic and physical properties of halogen: fluorine 9, chlorine 17, bromine 35, iodine 53, and astatine 85 being the atomic numbers. Astatine, they said it's a radioactive element, and atomic mass is 19, 35, 79, 126, and 210. The configurations all have a configuration of ns2 and np5, which is a last one electron. Just a minute. Okay, its properties. Atomic mass is 19. Okay, the configuration is ns to np5. The covalent radius increases as we go down the group, and the drastic increase from actually there is actually somewhat an increase. And ionic radius, if we see, it also increases regularly as we go down the group, and ionization enthalpy, it decreases as we go down the group, as it should be. And as far as I have seen, normally, mostly, like generally, if we take all the three groups are following the ionization enthalpy reducing as we go down the group. As for electron gain enthalpy, and it also increases, no, it, oh yeah, it increases as we go down the group. You can see that chlorine has a slightly lower negative enthalpy than fluorine, but if we consider negative enthalpy, it should decrease as we go down the group. Negative enthalpy, negative electron gain enthalpy decreases as we go down the group, with an exception of chlorine. Chlorine having slightly higher negative enthalpy than fluorine, but the trend is followed. As we see, bromine has a 325, whereas fluorine has 333. And electronegativity, if we see, fluorine has the highest electronegativity in not only this group but in all the elements of the periodic table. Fluorine is the most electronegative element. Then comes nitrogen, wait, no, not nitrogen, oxygen, with I think 3.5, and there is also chlorine with 3.2, and bromine 3.0, and iodine 2.7, which are fairly electronegative even as we go down the group compared to other elements of the same period, and astatine being 2.2, which is considered high for that period element. And as for hydration enthalpy, if we see, the fluorine has the highest hydration enthalpy, and the hydration enthalpy decreases as we go down the group, and there is a high difference of hydration enthalpy from fluorine and chlorine, and this difference keeps on decreasing as we go down the group. As for physical properties, Melting point, fluorine has a 57.4 Kelvin melting point. Boiling point is around 85 Kelvin. Density is 1.5. Distance, which is the F bond F, that is around 143 picometer, which is actually a large bond length for a second period element. Maybe it's because of electron-electron repulsion of fluorine. Bond dissociation compared to NO bonds, which are around 20 picometer, and other bonds from oxygen-oxygen bonds, which are around 128 or so. The fluorine-fluorine bond, which being at 143 picometer, is considered a bit large, and bond dissociation enthalpy being around 160, which is not as high as oxygen or nitrogen. Nitrogen being the highest single dinitrogen bond enthalpy, which is it's a triple bond. It is the highest and hardest to break, and oxygen is followed because it is O double bond O. But here F single bond F, so the enthalpy is kind of less here. But we see a sudden spike here in chlorine where it jumped by 100 approximately, and then it starts decreasing from bromine and iodine, with iodine having the least bond dissociation enthalpy. We can say fluorine and iodine are the least stable because of the least bond dissociation enthalpy, but this is on the general basis. And we can say chlorine is the most stable because of the high bond dissociation enthalpy, and the order is chlorine followed by bromine followed by fluorine followed by iodine. Iodine has such a small bond dissociation and such a less bond dissociation enthalpy. This is because iodine is a leaving group, and this is also due to the size of iodine being large compared to fluorine, as it has an atomic number of 53. Yes, 53. It has a large size, and due to that as well, it is having the least bond dissociation enthalpy. Bond dissociation enthalpy. Chlorine, we can say it does decrease as we go down the group, but with an exception of a special spike we seen. No, wait, we instead of saying that chlorine is irregular, we can say that fluorine is irregular, because chlorine is as it should be, but fluorine is irregularly less bond dissociation enthalpy. So we see fluorine is less, but from chlorine onwards it decreases as we go down the group, that is bond dissociation enthalpy. And as for standard electrode potential, fluorine has a really high standard electron reduction potential, and chlorine not so much, but it keeps on decreases as we go down the group. But they are all positive standard reduction and potentials, because they are all non-metals, and especially because they are halogens group. Under the halogens, they did not give anything much for astatine, because astatine is a radioactive metal and it will decay, allowing it for not providing our scientists enough time to read it. And we saw about polonium too, which is also only exists when uranium and thorium, a mixture of those, decays. And I believe there was something about half-life of it being around 13.2 days or so. I'm not sure if it is polonium half-life, but okay. The strengths of some of the atomic, physical and chemical properties are discussed below. Electronic configuration. All these electrons have some electron in their outermost shells and ns2np5, which is one electron short of the next noble gas. Atomic and ionic radius. The halogens have the smallest atomic radii in their respective periods due to maximum effective nuclear charge. Okay, halogens have the smallest atomic radii in their respective periods due to maximum effective nuclear charge. This is a basic trend. As we see, as we go from left to right of the period, the effective nuclear charge increases, the atomic size decreases. Based on that trend, the halogens, being the 17th group, having the highest effective nuclear charge, have the smallest atomic radius, followed by the noble gases. The atomic radius of fluorine, like the other elements of the second period, is extremely small. Atomic and ionic radii increase from fluorine to iodine due to increasing number of quantum shells. This is natural and it's a normal trend of the periodic table. Ionization enthalpy, they have a little tendency to lose electron, thus they have very high ionization enthalpy. The normally even though it is not a very stable configuration, the ionization enthalpy, when we compare to oxygen, which was around 1400, and for sulfur, which was around 1000, here fluorine has 280 or approximately 200 kilojoules per mole more enthalpy, and here for chlorine as well it is 200 more, and even for bromine and iodine, which are around 1000. This is due to the as I said before, the effective nuclear charge increases. Because of that, the ionization enthalpy also increases, and compared to the chalcogens group, they are high. I think even compared to the nitrogen, fluorine has a higher electronegative, not electronegative, ionization enthalpy, first ionization enthalpy, where fluorine is 1600, mostly 1700, nitrogen was around 1400, even though it had a half-filled stable configuration. Yes, nitrogen ionization enthalpy was only around 1400, but the halogens, if we see, the ionization enthalpy due to the effective nuclear charge even exceeds even the stability obtained by half-filled configuration, as it is all of them are above 1000 here, there, not here. And as for the chalcogens, if we see, chalcogens, the chalcogens have ionization enthalpy of oxygen, also has no, it has a little bit lower than nitrogen. Oxygen has around 1300, whereas nitrogen has 1400 as first ionization enthalpy. But fluorine, being very electronegative and also having the highest effective nuclear charge and having the smallest radius, has around 1700. They have little tendency to lose electron, thus they have very high ionization enthalpy. Due to the increase in atomic size, ionization enthalpy decreases down the group. Increase in atomic size, ionization enthalpy decreases down the group, as it should be. Electron gain enthalpy. Halogens have a maximum negative electron gain enthalpy in the corresponding periods. This is due to the fact that atoms of these elements have only one electron less than stable noble gas configurations. Maximum electron gain enthalpy in the corresponding periods. Okay, this is due to the fact that atoms of this element, okay, because as if we add just one more electron, they will become noble gas, as they have a desire or tendency to accept this electron. Because of that, they have really high negative electron gain enthalpies, as they desire for one more electron to become noble gas, as all of them without exception have such a configuration. If we see here, all of them have a 6p 5 np5 configuration, one more electron and they will become the next noble gas configuration. And as we saw in the if we see in the periodic table, fluorine, if one more electron, it will become neon configuration. Chlorine, one more electron, it will become argon configuration. Bromine, one more electron, it will become krypton configuration. Iodine, one more electron, it will become xenon configuration. And astatine, it will become radon configuration with one more electron. and we cannot say more about tennessine and afghanistan. I will leave them be for now, as they are radioactive elements. Elements have only one electron less than noble gas configuration. Electron gain enthalpy of electron elements of the group becomes less negative down the group. However, the negative electron gain enthalpy of fluorine is less than that of chlorine. It is due to small size of fluorine atom. As it is a small size, it cannot easily accept the electrons. Because of that, the negative electron gain enthalpy of chlorine is more than fluorine. As chlorine has a larger size, it can easily accept electrons. As a result, there are strong interelectronic repulsions in the relatively small 2p orbital of fluorine. They are explaining why fluorine has a lesser, even though it's more electronegative, why it has a lesser negative electron gain enthalpy. It is because of small size, which will cause electronic repulsions. The incoming electron does not experience much attraction. Incoming electron does not experience much attraction due to the repulsion. Electronegativity. They have very high electronegativity. Halogens are defined for electronegativity, at least mostly. The electronegativity decreases down the group. Electronegativity decreases down the group. Fluorine is the most electronegative element in the periodic table. Example: halogens have the maximum negative electron gain enthalpy in the respective periods of the periodic table. Why? They can easily accept electron because the next configuration is a stable gas configuration, which they tend to opt for or try to obtain. Because of that, they have a high negative electron gain enthalpy. Negative electron gain enthalpy being that when they accept electron, they will release energy, as releasing energy leads to stability. Because of such a reason, they are gaining stability. By gaining stability, they are releasing energy. Halogens have the smallest size in their respective periods and therefore high effective nuclear charge. As a consequence, they readily accept one electron to acquire noble gas electronic configuration. Then physical properties. Halogens display smooth variations in their physical properties. Fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid. Their melting and boiling points steadily increase with atomic number. All halogens are colored. This is due to absorption of radiation in visible region, results in excitation of outer electrons to higher energy level. By absorbing different quanta of radiation, they display different colors. This is also seen in D and F block elements as to why complexes gain colors. Similarly, the electron will absorb electromagnetic radiations. This will lead to loss of some light spectrum, and the reflection we see will be different. For example, F2 has yellow, Cl2 has greenish yellow, Br2 has red, and I2 has violet color. Fluorine and chlorine react with water. Bromine and iodine are only sparingly soluble in water, but are soluble in various organic solvents such as chloroform, carbon tetrachloride, carbon disulfide, and hydrocarbons to give colored ions, colored solutions. One curious anomaly we notice from table 7.8 is a smaller enthalpy of dissociation of F2 compared to the Cl2, whereas XX bond dissociation enthalpy from chlorine onwards show expected trend: chlorine higher, bromine higher, iodine higher. A reason for this anomaly, as I saw before here I was talking about how the here the distance between the XX bond, which fluorine has a it is about bond dissociation enthalpy. It is about bond dissociation enthalpies. Bond dissociation enthalpy about fluorine has only 160 bond, which is less bond dissociation enthalpy compared to chlorine, bromine, and iodine. Not iodine, but still close to iodine. That is the reason I said it's due to repulsions of fluorine being a small atom, Let's see what the actual answer is. A reason for this anomaly is relatively large electron-electron repulsion among the lone pairs in F2 molecule, where they are much closer to each other than in case of Cl2. Yes, same reason. Although electron gain example question, although electron gain enthalpy of fluorine is less negative as compared to chlorine, fluorine is a stronger oxidizing agent than chlorine. Why? It is due to low enthalpy of dissociation of FF bond. It can easily dissociate to become fluorine free radicals. High hydration enthalpy of fluorine. Hydration enthalpy decreases as we go down the group. So fluorine has the highest hydration enthalpy. I believe hydration enthalpy was when in aqueous state to vapor state or gas state, this is called enthalpy of vaporization, and this too for ionization. Then from vapor to again aqueous, we call it as hydration enthalpy. The energy obtained from conversion of gas to aqueous state, this is called hydration enthalpy. If it is negative hydration enthalpy, it is exothermic reaction where vapor to liquid is giving out energy. I think that is the case. Is hydration enthalpy the energy released when gas is converted to aqueous state of the solution? What is hydration enthalpy? Hydration enthalpy, also called the enthalpy of hydration, is the energy released when 1 mole of gaseous ions dissolve in water to form hydrated aqueous ions. It is a enthalpy change when gaseous ions are surrounded by water molecules via ion dipole interaction and form aqueous ions. This process is exothermic, so energy is released. Sodium, for a sodium, it is very high negative enthalpy. Not converting as, yeah, I understand that. One mole of gaseous ion getting converted into acid. Aqueous. As for high electron gain enthalpy of fluorine is less negative compared to chlorine. Fluorine is stronger oxidizing agent than chlorine. Why? Because it can easily break the FF bond due to low dissociation enthalpy and due to high hydration enthalpy, meaning when it is converted from gaseous ion to aqueous, it is releasing more amount of energy. As for how it is related to being a stronger oxidation agent, I am not too sure. Let's ask. Fluorine is a stronger oxidation agent than chlorine due to low bond dissociation of F bond F and F2, fluorine having higher hydration enthalpy. How so? Stronger oxidation, low bond dissociation enthalpy, very high hydration enthalpy of fluorine. It is negative? No, it is positive. Hydration enthalpy, yes, it decreases as we go down the group. Why fluorine is stronger oxidizing agent than chlorine is because lower bond dissociation enthalpy, bond is weak. Okay, therefore it takes less energy to break F2 into atoms than Cl2. Okay. This facilitates reduction gain of electrons. Higher hydration enthalpy of F after gaining electrons from very strong hydration interaction with water due to small ionic radius and high charge density. This releases making more energy, making the overall reduction of F2 more favorable. This releasing energy makes this reduction more favorable. This low bond dissociation enthalpy is needed to break this bond easily with less energy. This combined effect of more energy release and easier bond breaking, this will have a higher standard electron potential and be more strong oxidizing agent than chlorine. Okay. Chemical properties, oxidation state and trends in chemical reactivity. All the halogens exhibit -1 oxidation state. However, chlorine, bromine and iodine exhibit +1, +3, +5 and +7 oxidation state also, as explained below. Basically they are saying fluorine exhibits -1 oxidation state because it's the most electronegative atom. It cannot have a positive element, it cannot have a positive state, at least mostly. But however, chlorine, bromine and iodine and one more element was I believe astantine. Yeah, astantine, but they didn't mention astantine here. They are mostly studying about chlorine, bromine, iodine and fluorine. And chlorine, bromine and iodine exhibit +1, +3, +5 and even +7 oxidation state. How they do that is explained below. This is a basic configuration NsNp5. Okay, one unpaired electron accounts for -1 or +1 oxidation state when we fill electrons here. But first excited state, when one electron from the NPX or this is the NPX, NPY and NPZ orbitals, and in the ground state there are no electrons in the d orbital, but in the first excited state the paired electron in the NPY will go to the ND orbital. This leaves us 3 unpaired electrons. With this it can make 3 covalent bond, which will give us a +3 oxidation state, which can use this electrons to get a +3 oxidation state. And the second excited state where the NPX electron will again get displaced NPX electron will again get displaced into ND orbital. This will give a total of 5 electrons with a +5 oxidation state. And there is something else which is strange here. In the third excited state, it seems NS has one more electron which is in the opposite spin, and the ND orbitals have 3 electrons. This leaves us, but here even if that is the case, there should only be 3 electrons here. Maybe is it wrong printing? That might be the case. Even if that is the case, it will be 3 + 3 6. So the oxidation state should be +6. And I don't think S orbital can accommodate +3 electrons. Let's see if they mention anything about it. The higher oxidation states of chlorine, let's see above. All halogen exhibit -1 oxidation state. However, chlorine, bromine, and iodine exhibit +1, +3, +5, and +7 oxidation state. Also, as expected below, higher oxidation state of chlorine, bromine, and iodine are realized mainly when halogens are in combination with small and highly electronegative fluorine and oxygen atoms. This only happens, this +3, +5, and +7 oxidation state are only possible when they are these bromine, iodine, and chlorine are reacting with small atoms and highly electronegative atoms, which can only be either oxides, oxygen atoms, or fluorine atom, with fluorine being the most electronegative and oxygen being the second most electronegative. Example, interhalogens, oxides, and oxyacids. The oxidation states of +4, +6 occur in oxides and oxyacids of chlorine and bromine. We saw that here it is odd number itself, but even +4 and +6 also occur, which occur in oxides and oxyacids of chlorine and bromine. The fluorine atom has no d orbitals in its valence shell and therefore cannot expand its octet. Being the most electronegative, it exhibits only -1 oxidation state. All the halogens are highly reactive. They react with metals and non-metals to form halides. The reactivity of the halogen decreases down the group. The ready acceptance of an electron is a reason for strong oxidation nature of halogen. F2 is the strongest oxidizing halogen in its oxides and other halide ions in solution or even in solid phase. In general, a halogen oxidized halide. Okay, they did not give anything about here, which means most likely the configuration is NS1, NP2, I mean not NP2, NP3, and ND3 as well. This will give us 3 in the D, 3 in the P, and 1 in the S orbital. Total of 7 unpaired electron, which we have a possibility of having +7 oxidation state. This is not possible. 3 electron cannot accommodate in an S orbital. As for continuing, all halogens are highly reactive. They react with metals. They react with non-metals to form halides. The reactivity of halogen decreases as we go down the group. The ready acceptance of an electron is the reason for strong oxidizing nature of halogens. As they have high electronegativity, they can easily accept electron. This is the reason they have high oxidizing capability. F2 is the strongest oxidizing halogen and it oxidizes other halide ions in solution or even in the solid phase. In solid phase also, fluorine, if we pass it through, it will oxidize them. In general, a halogen oxidizes halide ions of higher atomic number. It even oxidizes the halogen groups, as it is the most electronegative. It can even oxidize its own group elements with F2 plus 2x minus will give 2F minus plus x2. This X can be chlorine, bromine, or iodine. And this is the same can be said with chlorine. It will also oxidize the other 2 elements of this group, of the 17th group, which are bromine or iodine. It will oxidize and make it as Br2 or I2. And same with bromine, it will oxidize 2I minus to give 2 bromide ions plus I2. The decreasing oxidizing ability of the halogens in aqueous solution down the group is evident from their standard electrode potentials, which are dependent on the parameters indicated below. What their standard electrode potential depends on. Half X2 gas, half mole of molecules, X2 molecules, 1 mole of X atoms or halogen atoms, half dissociation enthalpy will give gas, and this, what is this Eg, and this is ionization enthalpy, I believe. Yes, this is ionization enthalpy. No, wait, not ionization enthalpy. This is electron gain enthalpy. Electron gain enthalpy, dissociation enthalpy, bond dissociation enthalpy. This is hydration enthalpy. These are what make it standard electrode potential. This is what it depends on for standard electrode potential. The relative oxidizing power of halogens can further be illustrated by their reactions with water. Relative oxidizing power of halogens can further be illustrated by their reaction with water. They are giving the reaction with water. Fluorine oxidizes water to oxygen, whereas chlorine and bromine react with water to corresponding hydrohalic and hypohalous acids. The reaction of iodine with water is non-spontaneous. In fact, iodine can be oxidized by oxygen in acidic medium. Just the reaction of the reaction observed with fluorine. Basically, whereas all three of the atoms oxidize water, but iodine, having less electronegativity, is instead oxidized by water. The reactions are given below. Fluorine reacting with water will give fluor F minus, taking the electron from water, for giving 4H plus, and an O2 gas. And in case of chlorine or bromine, the gas bromine or chlorine gas will react with water to give HX, which is hydrochloric acid or hydrobromic acid, plus this is hydrohalic, and this is the reaction with iodine, where 4-iodine minus will get oxidized by 4H plus and O2, which will give iodine solid and 2H2O liquid. And now in the 17th group elements, we are going to study about the anomalous behavior of fluorine. In the nitrogens, we studied about the anomalous behavior of nitrogen, and in chalcogens we studied about the anomalous behavior of oxygen. In nitrogens, it is the ability to form, it is the lack of d orbitals, small size, electronegativity, ability to form 2 pi-pi bonds, 2 p orbital pi-pi bonds, and other elements. And in case of oxygen as well, it was small size electronegativity and the high electronegativity, which will it is anomalous behavior of oxygen. This anomalous behavior of oxygen. First is reactivity. A small size, high electronegativity, presence of strong hydrogen bonding. That's pretty much all for oxygen. Mainly due to small size and high electronegativity. Due to the high electronegativity, it can form so many compounds. Anomalous behavior of fluorine here. Like other elements of P block present in the second period of the periodic table, fluorine is anomalous in many properties. For example, ionization enthalpy, electronegativity, and electrode potentials are all higher for fluorine than expected from trends set by other halogens. Also, ionic and covalent radii, melting and boiling point, Enthalpy of bond dissociation, electron gain enthalpy are quite lower than expected. The anomalous behavior of fluorine is due to its small size, highest electronegativity, low FF bonding dissociation enthalpy, non-availability of d orbitals in its shell. Most of reactions of fluorine are exothermic due to small and strong bond formed by it with other elements, which will give them high stability. It forms only one oxoacid, while other halogens form a number of oxoacids. Hydrogen fluoride is a liquid. Boiling point HF is liquid. The boiling point is 293 Kelvin due to strong hydrogen bonding. Other hydrogen halides are gases. Reactivity towards hydrogen. They all react with hydrogen. H2SO4 had a high boiling point of around 600 Kelvin, but here, wait, H2SO4 is not related like this, but both are acids. Yes, reactivity with hydrogen. Halogens reactivity with hydrogen. All halogens react with hydrogen to give hydrogen halides, but affinity for hydrogen decreases from fluorine to iodine. As we go down the group, the reactivity with hydrogen decreases. Hydrogen halide dissolve in water to form hydrohalic acids. Reaction here, where it forms HX. React with water, dissolve in water to form HX. If it was chlorine, chlorine gas will dissolve in water to form hydrochloric acid. Some of the properties of hydrogen halides are given in table 7.9. The acidic strength of these. Let's see the properties of hydrogen halides first. HF melting point is 190 as we go down the group. No, it is kind of anomalous here. Melting point is HCl has the lowest melting point, the highest being iodine or HI, and HBr has the second lowest then fluorine. It is HI greater than HF greater than HF greater than HBr greater than HCl. Boiling point with fluorine being the highest boiling point, and boiling point increasing as we go down the group, except fluorine, which already has a high boiling point. Maybe this is due to high hydrogen bonding due to the electronegativity of fluorine. This was also seen in water where the boiling point was high. And bond length, it increases as we go down the group. This is common because of the increase in size. And as for dissociation enthalpy, HF has high dissociation enthalpy, and this dissociation enthalpy as we go down the group will decrease. And as for pKa, it is decreasing as we go down the group. The acid strength of this acid varies in the order. HF smaller than HCl, smaller than HBr, smaller than HI. The stability of this halide decreases down the group due to the increase in the bond dissociation enthalpy in the order HF. Okay, maybe they are saying HI has the highest acidic strength because it has the lowest bond dissociation enthalpy and it can easily liberate H+. But that is not so for the other cases because they have high bond dissociation enthalpy. Reactivity towards oxygen. Halogens form many oxides with oxygen, but most of them are unstable. Halogens form many oxides because both are electronegative atoms. This point we saw even in the oxygen 16 group elements where reactivity with oxygen. Fluorine forms two oxides, OF2 and O2F2. However, only OF2 is thermally stable at 298 Kelvin. These oxides are essentially oxygen fluorides because of the higher electronegativity of fluorine than oxygen. Both are strong fluorinating agents. O2F2 oxidizes plutonium to PuF6, and the reaction is used to removing plutonium as PuF6 from spent nuclear fuel. Basically, we removing that from nuclear fuel. Chlorine, bromine, and iodine form oxides in which the oxidation states are of these halogens range from +1 to +7, which we saw before. Combination of kinetic and thermodynamic factor lead to generally decreasing order of stability of oxides from halogens. I has the highest stability and Br has the lowest stability. Cl has the middle stability. The higher oxides of halogen tend to be more stable than the lower ones. Oxides with higher meaning iodine is more stable than the lower ones. Chlorine oxides such as Cl2O, ClO2, Cl2O6, Cl2O7 are highly reactive oxidizing agents and tend to explode. Maybe this is due to instability or instability. ClO2 is used as a bleaching agent for paper pulp and textiles in water treatment. We saw two explosives, I think two explosives in this chapter as so far, which are phosphine pH3 and here chlorine oxides, and of course third one is H2SO4, concentrated H2SO4. If we add too fastly in water, because the first dissociation enthalpy from H2SO4 to H plus HSO4 minus, this enthalpy is very negative. Because of that reaction is also explosive. And here chlorine oxide Cl are highly reactive oxidizing agent and tend to explode. ClO2 is used as a bleaching agent. Chlorine dioxide is used as a bleaching agent for paper pulp and textile and in water treatment. The bromide oxides Br2O, bromine dioxide, bromine trioxide are the least stable halogen oxides. Middle row anomaly and exists. Middle row anomaly, that's a new term. What is the middle row anomaly? What is the middle row anomaly? Second row anomaly, third period anomaly in organic chemistry, especially in to describe unexpected trends. Okay. It seems something more, but let's just remember it like that. It's better. These bromine oxides are very unstable and exist only at low temperatures. They are very powerful oxidizing agents. They are very unstable, so easily tend to release this oxygen and act as very powerful oxidizing agent. Just like how ozone, it was dissociating at the sea level to give nascent oxygen, same way these also dissociate to give oxygen and act as strong oxidizing agent. Existence of such compounds, because of the existence of such compounds, we don't say fluorine is the most strongest oxidizing agent, because very unstable compounds, they act even more powerfully many times than even fluorine. They are very powerful oxidizing agents. The iodine oxides I2O4, I2O5, I2O7 are insoluble solids and decompose on heating. I2O5 is a very good oxidizing agent and is used in estimation of carbon monoxide. Reactivity towards metals. Halogens react with metals to form salts or metal halides. For example, bromine reacts with magnesium to give magnesium bromide. The ionic character of halides decreases in order of higher the electronegativity, higher the ionic character. So as we go down the group, the ionic character decreases, where metal M is a monovalent metal. Monovalent meaning single valency. If metal exhibits more than one oxidation state, the halides in the higher oxidation state will be more covalent than the one in the lower oxidation state. Higher the oxidation state of the metal, the higher the covalent nature, lower the ionic nature. For example, tin chloride, lead chloride, lead tetrachloride, tin tetrachloride, and antimony pentachloride, and uranium hexafluoride are more covalent than tin dichloride, lead dichloride, and antimony trichloride, uranium tetrafluoride respectively, because they have higher oxidation state, and because of this higher oxidation state they show more covalent nature. Then reactivity of halogens toward other halogens. Halogens combine amongst themselves to form a number of compounds known as interhalogens, and we saw about a reduction or oxidation capacity of halogens themselves, where we saw that fluorine can oxidize all three of the remaining three of the elements, and as we go down, the number of elements it can oxidize also decreases. And these are the compounds formed between halides or halogens. These are called interhalogens. These can be of types X, X dash, X, X dash 3 times, X, X dash 5 times, and X, X dash 7 times, where X is a larger size halogen and X dash is a smaller size halogen. Fluorine exhibits only -1 oxidation state, whereas other halogens exhibit +3, +1, +3, +5 oxidation state. Explained. Because fluorine lacks d orbitals and it is the most electronegative atom. Because of that, it only exhibits -1 oxidation state. Fluorine is the most electronegative atom and cannot exhibit any positive oxidation state. Other halogens also have d orbitals and therefore can expand their octets and show +3, +1, +5, and +7 oxidation states. In text questions, considering the parameters such as bond dissociation enthalpy, electron gain enthalpy, and hydration enthalpy, compare the oxidizing power of F2 and Cl2. I saw this parameter such as I basically had a doubt in this question and asked it as well. Basically, what they are saying, chlorine, there was a question in text question, example question saying that chlorine was stronger oxidizing agent than fluorine, and answer was it was due to fluorine having a lesser bond dissociation enthalpy and higher hydration enthalpy than chlorine. And they gave how this standard electrode potential depends on what it depends on. It depends on bond dissociation enthalpy, electron gain enthalpy, and hydration enthalpy. Because of such a reason, because of all those reasons, where fluorine has a lower dissociation enthalpy, lower electron gain enthalpy, and higher hydration enthalpy. Because of this reason, the oxidizing power of fluorine is higher than oxidizing power of chlorine. Give 2 examples to show the anomalous behavior of fluorine. Anomalous behavior of fluorine is due to its small size, high electronegativity. What its behavior anomaly can be? The anomalous property is the low F bond dissociation enthalpy and non-availability of d orbitals. And most reactions of fluorine are exothermic, which will provide stability for the compound. It forms only one oxacid, while other halogens form a number of oxacids. Hydrogen fluoride is a liquid due to strong hydrogen bonding. Other hydrogen halides are gases. These are all the examples for showing the anomalous behavior of fluorine. C is the greatest source of some halogens. Commands basically this is on the first topic under the 17th group. No wait, the second topic under the, no, it is the first topic under the 17th group, which is occurrence. The C is the greatest because we find many salts, the salt with the NaCl being 2.5% or so by mass. It contains chloride ions, halogens, and there are many other animals containing iodine salts or other salts in their bones or shells, etc. Basically found as CaF2, fluorospar, cryolite, Na3AlF6, and fluorapatite. Small animals. Seawater contains chlorides, bromides, and iodides of sodium, potassium, magnesium, and calcium, but is mainly sodium chloride solution, 2.5% by mass. The deposits of dried up seas contain about these compounds: sodium chloride, carnallite. Certain forms of marine life contain iodine in their system. Various seaweeds, for example, contain up to 0.5% iodine, and child saltpeter contains up to 0.2% sodium iodate. Yeah, those are the answer for the in-text question. Then we are going to see preparation. It seems I don't have time right now. I'll be ending the stream.